Hello everyone. Today we'll be going over the concept of databases within our first lecture series. So to be able to give an overarching concept, we're going to be breaking down every single step accordingly between the concept example, and two practice problems to be able to go over the entire system design interview process, but not just the interview process, but getting a further understanding of how to build data intensive applications as well. So to be able to get started, I'm just going to also do a different color over here. Data systems are basically the backbone of modern applications. They are often slightly orchestrated without us even knowing about that we are interacting with them on a daily basis. At their very core, they encompass a diverse set of tools. Each are designed to handle specific types of data operations. These include databases for structured data storages, caches for high-speed data retrieval, and queues for managing asynchronous data, so to be able to write out the notes. We have databases, which is used for storage. We have caches, which are used for high-speed data retrieval. And then we have queues, where they manage asynchronous tasks. And while databases are optimized for data integrity and complex queries, caches focus on speed, storing frequently accessed data within memory, while queues, on the other hand, ensure that the tasks are processed in an orderly fashion without overloading the system altogether. So overall, the real magic happens when these components are woven together into a cohesive whole. This integrated approach allows each tool to play its own strengths, creating a system that is more than the sum of its parts. For instance, a cache may sit in front of a database, delivering rapid responses to read operations, while a queue can handle background tasks like sending emails without affecting the user experience. By thoughtfully combining these tools, developers can build complex, high-performing, and reliable systems. But the complexity doesn't end there. The interconnectedness means that developers must also become architects, ensuring that the entire system functions harmoniously with reliability, scalability, and maintainability in mind. They must consider how data will remain consistent across different components as well. So, to be able to go further in depth, we have to consider reliability, scalability, and maintenance. Altogether, reliability, scalability, and maintenance. By overall focusing on how to consider how the data will remain consistent across the different components and how the system will perform under high load and how it can actually evolve over time without becoming a maintenance nightmare. This is overall the art and science of data systems, where strategic planning meets technical expertise. Now, let's consider a concept example. So let's consider a social media platform as an example of a data system. This platform needs to store vast amounts of user-generated content, serve this content quickly to millions of users, and process a constant stream of new posts and interactions. To achieve this, the system might use a relational database to store user profiles and posts. So just to be able to highlight it. An in-memory cache like Redis could be employed to keep the most popular content readily available for quick access, minimizing database loads. Meanwhile, a messaging queue like RabbitMQ could manage the flow of notifications and updates, ensuring that the processed efficiency are in the right order. So if we use a cache, we could use a memory call. status. And then for queues, and when a user updates their profile, the application code writes the changes to the databases. At the same time, it invalidates a corresponding entry in the cache to prevent stale data from being served. The next time someone accesses the profile, the cache triggers a fresh read from the database, updating the cache with the latest data. And additionally, if the user's actions generate notifications, these are sent to message queues, which dispatch them without affecting the main application's performance. Overall, by delegating different responsibilities to specialized components, the system maintains a high performance and reliability, even if it scales to accommodate more users and data. This illustrates the practical application of data system design principles, creating a harmonious balance between functionality, scalability, and maintainability. So now let's dive in straight into a practice problem. So let's imagine that we are building a data system for online travel booking agency. So the system must manage hotel bookings, customer reviews, and real-time availability updates. A relational database stores the booking details and customer data, ensuring transactional integrity for reservations. And meanwhile, a separate document-based database might hold user reviews for easy retrieval and analysis, while a cache ensures that the most frequently accessed hotel information is available for immediate display. So, a user books a hotel room, and the application code must execute several steps. First, it writes the booking details to the database and ensuring that no overbooking occurs. Next, it updates the cache so that way the next search reflects a new availability status. Simultaneously, a message is published to a queue to process the payment and send a confirmation email. And this queue ensures that the payment processing system is not overwhelmed during peak booking times. So, if we're going to go over this overview, I'm just going to change a different color over here. We're going to need a number of things. So our workflow diagram is going to consider the following points. So one, we need to consider the user action. Then we are also going to consider the initial validation. Then the queuing. There we go. For transaction execution, slash database update, with the next part being order fulfillment, data synchronization, slash cache update, and then also user notifications. And trade confirmation. So if we're going to be going over each of the following components, just for the whole travel agency, we're going to have to understand their underlying components. So for user actions, we're going to have to, and I'm going to change a different color for this, So what we need to do is that a user books, for instance, a hotel on the platform. The initial validation, or the trade validation, will be ultimately deciding the application server validates the booking. So you'll have the server validates booking. Then queuing, the booking details are placed in a high output messaging queue to keep track of the transactions. Then for transaction execution and database updates, the booking is dequeued meanwhile the database transactions begin. Updating booking details. And in the case of order fulfillment and trade execution, we receive confirmation of the reservation. And data synchronization and cache updates to present real-time information. After the transaction, the cache is updated. So and for the second part, the customer receives a confirmation notification. So and it could be a message, an email. So these are the 7 steps that we would need in order to actually get through to be able to build our database system. I'm also going to put the example notes down for when we are presenting each of the practice problems at the same time for reference. They'll be pinned in the comments section. So we can zoom out. All right. Now in our second problem, let's consider an online multiplayer game with a virtual economy and virtual world in particular, where players interact with each other at different stages and different levels. So overall, whenever we are constructing the data system must manage the game state, player interactions, and virtual transactions as well if they ever want to make in-game purchases for weapons, suits, or any other type of armor. So for instance, the database we may use would be a NoSQL database, which could be ideal for storing flexible data model of a player's states and game items, while meanwhile the caching layer would be responsible for holding the current state of the game world, providing low latency access for the gamer's server. And meanwhile, a message queue might be used to handle tasks such as matchmaking, broadcasting game events to players, and processing in-game purchases all together. So overall, we need to develop scenarios for player-player interaction or player-player trading system or player-player kills, and understand between just the data flow in of itself between how players may buy armor, games, or also messaging at the same time. So after we have these 3 different components to be able to consider what we may use, so I'm just going to list out what we would use. So for instance, a NoSQL, caching in of itself, be just a layer. and a message queue. So overall, our workflow is going to be going about in the same similar steps that we have already seen in the previous example. Just going to change the color over here. We got to consider the initiation of when the game starts and the player is interacting between one player to another. For instance, maybe shooting or maybe trading different items to be able to start. We need to consider the validation of the transaction in of itself, the queuing, the database transaction, so it stores the event. The execution of the items. The synchronization. / cache update. And then also we need to consider the confirmation. And I'm also going to add something a little bit more extra to even consider at the same time for in the cases of failure handling. But to be able to go over our workflow, what we need. So for the initiation, that will be, for instance, and I'm going to change a different color over here. It's going to be player, shooting player, for instance, or trading items. The validation of that will be the game server validates. The queuing in of itself will validate the trades. It could be a time series, for instance, time series stamps. The database transaction. Actions are stored between players. It could be kills between them, or the number of kills, and also state. It could be different counters at the same time. The execution will be details over the action. Synchronization with cache update. So if you're doing a live player versus player event in of itself, and you have a counter between the two, there will be cache updates to reflect the state of the game. So okay. So, cache updates for state of game. And finally, the confirmation for this is going to be player receives notification of updates within game. Now, since we already have a similar pattern that we've already seen from the previous example into this one right now, so based on the 7 workflow diagrams aspects, there could also be event states that we need to also consider, or edge cases all together. So we need to consider at the same time what would happen if we were to have the entire game crash all of a sudden, or different cases of failure. So how will we handle the given situation if a game were to crash or something were to be able to crash? Well, there are three components that we need to consider at the same time. We need to consider the software failure. We need to consider hardware, and then human error at the same time. So what we need to do to be able to actually consider the points of failure is this system that we need to consider, which would be the validation of the failure to ensure that there is some baseline prevent errors, and this can be applied for software, hardware, or human interactions at the same time. Another one would be queuing, checking the queue between the different states. And we can also look at the database transactions. And finally, we can also check the caches as well to see the updates. So we have validation, queuing, database, and caches as well to handle our points of failure. So let me just take care of this part. And so yes, this is the second practice example that we would have to be able to understand the full basis between system design. Thank you very much for taking time to be able to watch this. If you found this useful and helpful, feel free to like and subscribe at the same time. And if you have any other questions about data systems for our first introductory fundamental basis of it, by all means, feel free to put the question in the comment section below. And as always, take care. Cheers. Bye-bye. Hello, everyone. Today we will be going over the concept in data systems called reliability, and overall just reliability in software systems. So inside of the world, within the concept of reliability, reliability is the backbone of user trust and functionality in the digital world. At its core, software reliably revolves around the system's ability to function under extreme conditions, handle errors gracefully, and maintain performance standards without unauthorized access and misuse. Now, faults and failures are the yin and yang of system reliability. Faults are deviations in components from their speculations or specifications, while failures are the unfortunate occasions when the system as a whole stops serving its purpose. Fault tolerance is our safeguard against these. It's our digital immune system, designed not to prevent every possible mishap that would be impractical, but to keep the system running despite them. The principle is to design systems so robust that faults don't escalate to failures. Now, a good vivid example is actually now part of the Amazon Web Service logo in of itself. This is actually known as Netflix's Chaos Monkey, which is a popular open source reliability system. And you can also Google it as well, just to be able to find different packages about it. It's basically used as a vaccine for the system. Scene for data systems, where it's able to do a check and balance type of methodology to be able to check for different faults within a given database system that would be either exploited, and also provide a further backbone for a system's resilience. In of itself, it is a counterintuitive method of breaking things on purpose to make them stronger. So in particular, if we can just give one example, say for instance that it could give a brute force approach for either a hardware failure or a software type of failure. In of itself, the Netflix Chaos Monkey will try to see faults within a system to be able to try to make them robust over time. So as we move forward in just storage systems, initially from just relying on storage systems to cloud-based solutions. So as we scale up and move to the cloud, there are going to be an increase of number of machines. We therefore also increase our potential for hardware failure since we already have more servers that are basically serving more users in itself. And so what needs to happen is that there needs to be a redundancy in the traditional process of having backups ready to step in. However, as we have new paradigm shifts between new forms of computing, we need to figure out exactly how to tolerate the loss of an entire machine with software fault tolerance strategies, allowing for things such as rolling upgrades without downtime. But there's also more reliability than just handling hardware issues. Software errors and human errors are equally potential threats. So overall, for our errors, we would typically have hardware, software, and human. Hardware typically means systems shut down. Software can refer to a bug. Then human can refer to triggering a system by either hardware or software faults. So software errors, if we want to be able to go over them in particular, software errors often stem from systemic bugs lurking just within the shadows and waiting for the right combination of conditions to occur. And to be able to combat this, there's a whole isolated testing process. To be able to help mitigate and actually test for those robust errors and try to create robust solutions as a result. And overall, with human errors, if we want to go over them, there could be a series of heuristics and misconfigurations that may in of itself override a system without us even knowing. And so what we need to do is that we create sandbox environments for safe experimentation. Where in of itself we can actually understand between the human conditions and enable quick recovery and have clear monitoring for every possible warning sign. Overall, reliability isn't just for mission critical applications, it's just for general expectation when you ever have a data intensive type system. So if we want to go over a concept example that we're going to go over the case of a power grid outage scenario. So now let's just imagine that we have a power grid and management software. It is designed to handle the complex interplay of electricity supply and demand across the vast network. Suddenly, one stormy night, a lightning strike causes a critical server to fail. This is a fault, a deviation from the server's specification to be operational because we have lightning. That's bad. Now, if the software managing the grid is fault tolerant, the system immediately switches to a backup server without interrupting the power supply. No failure occurs in the overall power grid system despite the fault in one of the components, and everyone goes home happy. To further strengthen the system, the power company regularly conducts failure drills. Putting it here. Put a different color. Similar to Netflix's Chaos Monkey approach, they simulate server failures to ensure that the switch over to backups is seamless and the fault-tolerant mechanisms are always ready. Another key aspect is dealing with software errors. So let's just go over exactly. So we have hardware. I'm just going to use a different color. 1 second. There we go. So hardware, we'll just put in Netflix Chaos Monkey. One key for backup. Transition. As in, there are loads of simulations already set up in place where if hardware fails, it already knows exactly where to go. It's been tested multiple times. Now, for the software aspect, let's just say that there's a bug overall and it controls the power distribution. It assumes that energy demand is constant, which is not the case because it can, since we're dealing with an electricity system, demand is going to be sporadic depending on exactly where it's being allocated. And during peak usage, the assumption leads to overloading and failures in the network. And this is a systemic software error. To prevent such a scenario, the company implements a rigorous testing and real-time protocol. So, testing and real-time protocol. There we go. In order to actually isolate those scenarios and then implement rigorous testing and real-time monitoring to detect and rectify such flawed assumptions before they cause real issues. Lastly, we're going to tackle human error. Where operators in the control center might incorrectly configure the system during maintenance, causing an outage. To prevent this, the system is designed with intuitive interfaces, which has robust testing environments that allows for a quick recovery for the missteps, minimizing the impact of human errors. So, intuitive systems. With robust testing. Easy use. So yes, overall we conduct failure drills between the hardware, software, and human errors in itself to think holistically over the impending cases of faults and failures in of itself, and how do we mitigate them for the whole data system. So let me just zoom out for a second so you can get the whole picture. There we go. All right. Let's write this here. There we go. Where hardware, software, human error. Now let's look at a practice example to be able to cement our following concept. So say for instance that we're working with a stock trading app. So if we want to build a reliable system, there are a number of steps that we have to take in order to actually be able to build out the system. And as you notice, I already have a series of different components I'll be breaking down throughout the rest of the entire time. So going back from a previous lesson, in order to actually have a data system in of itself, the data system must have a database. And it could be any kind that we want. It could be a cloud-based one, such as it could be Firebase, MongoDB, Azure, Amazon Web Services, just to name a few. And but then what we need to do, just within our following database, is that we also need to connect with cache and also queue to keep up with updates of the data in of itself. So the first step that we really need, once we have all three of these components, is that first we got to understand. I'll use a different color. One, we got to figure out the data flow. Two, design for reliability. Third, being handling failures. So If we were to have a cache system, a popular one is typically Hazelcast to be able to update real-time data as there are new trades already going in and out, because the trades in of itself would represent parts of the queue in of itself of different time sequences that we would have. For instance, whenever we lock a trade, buy a stock, sell a stock, for instance, we would use, we can use Apache, Apache's Kafka, actually, that's the name of it. Which we use as a queue to be able to handle the flow of trade orders that we would make for buying, selling, and or shorting, or options or futures, namely, while Hazelcast would actually be representing for the caches in real-time systems. Now, in order for us to be able to actually communicate between the data flow and understanding between high-performance trades and understanding just the whole user actions that we would have based on our three components for the data system, when designing for reliability, each of the components must be identified, and we must integrate fault tolerance for each of the components. For the database, we implement redundancy, perhaps with a master-slave configuration as one dynamic. So if the master fails, a slave can take over without the loss of the service. The cache system would be distributed across multiple nodes to handle a node failure. And for the message queue, we ensure that it's robust against message loss or duplication, even during faults, by using transaction logs and replication. And meanwhile, for handling failures, what we would have is that we plan to handle failures all across the whole system. And if a component goes down, whether in hardware, software, or human error, we're able to reroute the task to implement healthy components, and then we also make sure that we isolate those tests so that way those tests would actually be robust enough to be able to handle out different scenarios if a system goes down. If the primary database fails, the system should fail over to a replica with minimal downtime. A mechanism to retry or compensate for failed operations must be in place for the messaging queue as well, and also for our cache at the same time. So then what we need to do is that we need to implement recovery protocols as well. Where that way we train on hardware, software, and human errors. So that way, we implement recovery in the case of a fault. The system needs to recover gracefully. And if the database server, for instance, crashes, it should automatically restart and recover from the logs. If a cache node fails, other nodes should be able to take over the load while it's being restored. And also, we implement recovery protocols for queues as well, if there is some type of system backlog, or maybe there might be some type of error we don't know of. And finally, what we need to do is that we need to implement a design workflow, hence what is right over here. So, 5, implement design workflow. So these 5 steps, we have to understand the data flow, then design for reliability, so we know the faults, and handling failures, knowing what to do. Then we implement the recovery praise, and then we implement the design workflow, which is right over here, namely. So let me just zoom out of this to be able to help give the bigger picture that we have. So yes, this will be just how we go through a basic practice scenario for these 5 different steps, and also going back from our previous lesson as well, knowing that, oh hey, to create a database system, we need to create a data system, we need a database, we need caches, and we also need queues as well to be able to build out just different components that way we already can build our data intensive applications. But then we also need in the case of reliability, we have to implement these series of steps to be able to know exactly what to do. And let's put this Apache Kafka. Sorry about that. Yeah, so Hazelcast is the cache, Apache Kafka is the queue, databasing can be whatever, and then we go through the series of 5 steps to be able to know exactly how our data is going to be flowing, and also putting out different series of edge cases and faults needed. Now, for our second practice problem, let's focus on a multiplayer game and focusing on the data flow for an online multiplayer game. For our second practice example, we're designing a data flow for new features in an online multiplayer game, a player-to-player item, first-person shooter game. This requires a series of managing different series of states between player interaction and ensuring that the virtual economy in of itself remains intact. So the first thing that we are going to need to do, well, first off, we have to know exactly what a whole database is consisted of. So a data system is consisted of a database, cache, and queue. So having those 3 components, we'll be able to create our data system. But then the way how our data flow is actually going to be done, we're going to go back on our 5 steps that we built from previously. And so what we need to do is that we can use, for instance, in understanding our data flow and understanding how the database, cache, and queue are actually going to be coinciding with each other. And I also have a handy visual over here to be able to help solidify it. Let me see if I can magnetize this for you folks. There we go. So you have your clients that authenticate, they go to different services, and they can go throughout different matchmaking. There's a fleet of them all together. It interacts with the API, and then gets to the database. Over here, there we go. So our 5 steps that we need in order to actually be able to create our, to understand more about the reliability of our given multiplayer online playing system, is that the first step we have to identify data flow, understanding, or I'm just going to put down understand the data flow. Understand the data flow. How it's all going to interact. We can use different components between different databases that are on the market, caches and queues, to be able to build up our whole data flow. And then we would facilitate different actions that players would use in a team first-person shooting environment, for instance, for a video game right here. And then the second step that we would need is to design for reliability. So and third is that we need to ensure consistency and handle failures. And implement recovery failures, implement recovery protocol, and then design slash visualize the workflow. And when we are implementing recovery protocols, we always focus on the hardware, software, and human side. So if we are going to be going every single part of our steps that we have for online multiplayer function that we have for our flow, is that we need to understand the data flow and identify what data is required to facilitate different actions for users. And then for step 2, when we are designed for reliability, we would handle in of itself the different actions that we would have. So we would understand between the interactions between the database, caches, and queues over how they would manage different states for taking off different actions that players would have. And they would handle failures in the case of whenever there must be another error that has already occurred, or different heuristics that we would see for systems to be able to roll back on hardware failures, or be able to isolate and test different software components for bugs, and then also for human interaction, implement our sandbox method as well. And then finally, for our implementing our recovery protocol, once we have handled the failures and identify, we would look from the hardware, software, and human side of how we would implement them to be able to isolate and test, and therefore be able to put them out inside of our data system. And finally, we will design and visualize the workflow over how our whole system would coincide and interact between the multiplayer environment and handling such failures. So a multiplayer game architecture, implement, handling failures. So let me just zoom out of this to give you a bigger picture. There we go. Okay. So we have our 5 different steps for our second practice one. We understand the 3 different components for a data system. Where it encompasses a database, cache, and queue. We can use what is already available to handle different various series of events. And then we have our 5 different steps that we use, solely focusing on reliability. Understand the data flow, design for reliability, handle failures, implement recovery protocol for hardware, software, and human interactions, and finally we design and visualize a workflow that we have over here to handle such failures. And so yes, this was system design, building data intensive applications, lesson number 2, focusing on reliability. Thank you again for taking time to watch this. If you found this playlist helpful, and you also found this video helpful, be sure to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everybody, today we're going to be going over our system design course, particularly focusing on the concept of scalability. Now, to be able to give a breakdown over the concept of scalability, in the digital world, the concept of scalability is overall crucial to build a foundation for whatever application that we are building. It's a concept in of itself where it ensures that a system gains popularity over user base over time. And while also scaling, it doesn't crumble under its own success and have a series of faults and failures as the system continues to grow. So imagine building a bridge that was designed for a few cars, but is now faced with a relentless stream of heavy traffic. Scalability is an engineering principle that anticipates and accommodates this growth without the bridge giving away. Now, scalability refers to the capacity of a system to handle a growing amount of work or its potential to enlarge or overall accommodate that growth. A system's architecture defines its scalability. A scalable system is flexible, resilient, and capable of increment loads. Incrementing loads without performance deterioration. And scalability in of itself is not considered binary. It's not about whether a system can scale or not, but about how it scales. Can it grow horizontally by adding more machines, or vertically by adding more power to existing machines? There are two concepts of horizontal and vertical. Where vertical is focusing on the present resources of the machines, and horizontal means just extending that pool of resources as well. And to give a vivid example for a concept, let's consider a website that originally serves a small regional customer base, but as the company grows and attracts a global attention, its user base is going to obviously grow exponentially. Will the original server's setup actually be able to serve that expansion? And was it perfect for a few hundred visits a day? And can it support thousands or even millions of users? And this is where scalability comes into play, determining whether the website can maintain its performance as the number climbs, or handling the question if the scenario of possible crashes occurs, leading to the pressure of the website to actually go down, or leading to downtime and therefore the loss of trust of users. It could be, for instance, on websites with loads of traffic and then it doesn't have the capability, the databases, caches, and queues needed to be able to maintain its data system in of itself. So going back on our concept as well, we always need, for a data system, let me just move this over here. A data system must always have databases, caches, and queues. Those three components are crucial to be able to build our data system. And the question is, can the present resources actually be able to handle it as our application continues to grow? So in the context of this, it's critical to understand for planning for scalability for not just technical issues, but it's also a business imperative. It's about ensuring customer satisfaction, maintaining performance standards, and safeguarding the system's availability, all while keeping costs in check. A scalable system is not just about handling the load today, it's about predicting the load of tomorrow and being prepared for it. So overall, preparing for and so let me just scale out of this. And so, yes, this is our given concept. Now, to solidify our understanding about scalability, let's take a really good example. So let's just take a big social media platform such as Twitter, formerly known Twitter, now X. So in order to solidify the concept of scalability, the social media platform, Twitter/X, has seen astronomical growth since its inception, now handling an avalanche of tweets and interactions daily. Twitter users grew from tens of thousands to hundreds of millions, presenting a textbook case of scalability, challenges, and solutions. In 2012, Twitter was averaging 4,600 tweets per second. And if sometimes influx all the way up to 12,000 tweets a second. But the challenge wasn't just in the volume of tweets, it was the fan-out nature of these tweets. A single tweet could potentially be delivered to millions of followers, so the question wasn't just about handling 12,000 tweets per second, it was about managing the distribution of those tweets to followers' feeds. A significantly heavier read load, estimated at 300,000 requests per second for home timelines. So all those tweets will go out to specified followers, and we would have 300,000 of them, for instance, that would be on home feeds. And as we know, between database systems or data systems as a whole, they require a database, cache, and queue. And throughout each of the steps and processes, we had to understand the data flow between all the interactions all together. And so Twitter's answer to be able to solve this heavy load time and heavy amounts of data being transported was to develop two key strategies. First, they needed to optimize the data flow and data pipeline by implementing an efficient storage and retrieval system for tweets. So we would focus on the data pipeline, and so we would have to consider, since we would need to ensure that users multiplied as they were being added onto the system, they wouldn't be waiting on slow timelines. Secondly, they also needed to update the caches throughout every single tweet that was also being added. So what they needed to do, needed to be updated. So moving over here. So what they would need to do is that they needed to store tweets in a way that when a user tweeted, their message was initially pushed to the caches of all their followers, making timeline loading a breeze for the end user. So in essence, Twitter had to ensure that their infrastructure could handle not only the growing number of users, but also the number of tweets and their interactions with those tweets. Their solution showcases how scalability goes beyond just mere capacity. It's more about the design and capabilities of how to handle the data flow from every single user interaction, so that way we can prevent failures and faults altogether, to handle the data efficiently and to harmonize the entire process between the initial small group of users to then scaling at an astronomical rate. And so we need to consider different processes altogether to understand the data flow, as well as how that data is going to be handled. Now let's dive into a practice problem to deepen our understanding of scalability through the lens of a real-time stock trading application. This application must handle the momentum of the following tasks to process thousands of transactions per second. And instantly upon updating those transactions, those balances also need to be reflected and providing real-time feedback to users. And a data system must always abide by the following tools that we need. We need a database, cache, and queue. And understanding the data flow between all of them to be able to mitigate any failures and faults that we would have throughout our database system, as well as designing a workflow that would help us be able to understand exactly what services we're using to be able to create this real-time stock trading app. So in order for us to be able to develop this robust data system, we need to imagine a database serving as a financial ledger financial ledger. The database will meticulously will be recording trades and account movements, and this is complemented by distributed cache that will update consistently per trade and offering up to the second stock prices and the account balances with minimal latency, and it would therefore empower traders to make swift, informed decisions. And finally, a messaging queue to orchestrate the flood of trade orders, ensuring that each is processed accurately and in the sequence. So in order for us to be able to create our workflow diagram, I'm just going to do a different color. The steps that we need to do to be able to create this are going to be the following. One, we need to understand the user interactions. Then we need to message queue handling. And reflect the database transactions. Finally, we have the following two. Sorry about this. Then we will handle database transactions. Implement cache updates. And then consider failures protocols. Failure and fault protocols. So, in order to go over each of the following steps that we have, we would need to consider the following five. One, for the user interface interaction, traders place an order via the application's interface, where seamless user experience is critical, and the system immediately acknowledges the order to uphold to the trader's trust in the platform's efficiency. Meanwhile, the messaging queue handling would, upon every single order that is placed, it is routed to a message queue like Apache's Kafka, and this step is vital as the queue acts as both a buffer and an organizer, ensuring that trades are processed sequentially, thus maintaining the transaction integrity. And while we have the message queue, the database transactions have orders reflected upon every single trade and transaction, since we already have an influx of users that are making trades between buying and selling different stocks in real time. The order transitions from the queue to be executed by the system, and the database then updates the ledger that we have up here. Let me just fix this. The database will update the ledger consistently and adjust the account balances accordingly. And this phase highlights the importance of consistency, ensuring the transaction is entirely successful or aborted. And meanwhile, every single cache to update real-time information is concurrently working together with a database to refer to the display of the latest account balances and stock prices, ensuring that the traders see accurate, up-to-date information. And meanwhile, we need to consider the different heuristics of failures and faults while we are building this data-intensive application. And the system is engineered to manage failures smoothly with protocols in the hardware, software, and human side. So that way we can ensure that no trade is lost and consistency is maintained upon further recovery. The system reconciles dependencies across the cache, database, and message queue accordingly to reflect all the accounts, transactions, and such. So let me just add some further notes at the same time. software, and human side. Let me just clean this up. And so, yes, this would be our stock trading platform. Let me just zoom out further. There we go. And also get rid of this. For our next exercise, let's consider an online multiplayer game with a vibrant economy of players. So here, the concept of scalability is tested by the dynamic game world, including player interactions as well as their actions as well. The system manages their game states, player actions, and overall the whole in-game system. So we always need three different parts to be able to create a data system. We need a database, cache, and queue. And so what we could use for our database would be something like a NoSQL, which is adept at handling the constant evolving data model of player states and game items. And we need a caching layer, maintaining the current game world state, offering rapid access for game servers. So we need a cache layer. And then a messaging queue, which facilitates various tasks such as matchmaking, events, broadcasts, and transactions being processed. So where it's handling, I'll use a different color. Updates in game. And so in order for us to be able to facilitate scalability, the following steps that we need to include are going to be to consider the user interaction, the cache updates, messaging queue, failure and management protocol, and finally the recovery protocol and validation. So going over each of the following steps, for user interactions, we would have the player actions already set in place where it's easy and seamless. So we have easy and seamless interaction. Cache updates, game updates per action. Messaging queue. That's confirming. Failure management protocol. We need to consider the following faults so that they don't transition to errors. And we need to consider the hardware, software, and human testing protocols. And we also need the we need system integrity, for logs, and finalizing actions. Overall, we are checking for edge cases. So yes, let me just zoom out of this to give you all a clear picture. And let me just rewrite this to be able to make it clearer. There we go. And so yes, this was our video on how to build data-intensive applications focusing on the concept of scalability. Thank you again for taking time to watch this. If you have any other questions or comments, feel free to put them in the comment section. And if you enjoyed this video, be sure to like and subscribe. And as always, take care. Cheers. Bye-bye. Hello everyone. Today let's go over the concept of data loading and then understanding system load and scaling challenges. So when we're discussing about data loading or system loading, it's crucial to capture the current demands on the system with precise metrics known as load parameters. Largely because since computers operate in binary, they are going to have different moments of data that is going to be uploaded between all three of their components, between a database, cache, and queue, and have their system update in real time. And so these parameters are pivotal to understand how the system is performing and to predict its behavior under future growth. A system's load can be quantified in several ways, depending on the architecture, such as requests per second, read-write ratios, in the database, active user counts, or cache hit rates. Identifying whether the system's average performance or its behavior under extreme conditions is more significant to your scenario is overall a fundamental step in designing a robust system. To contextualize these concepts, let's consider the example of Twitter again and seeing the entire encompassing scope of how their system loads while also scaling with the vast amount of users that they have. For example, Twitter has large amounts of tweets per second. And therefore, with a large amount of tweets that they have per second, they roughly have about 12,000 posts per second. The challenge for Twitter comes from the fan-out effect of what they have with these 12,000 tweets per second. For every single 12,000 tweets per second, there has to be a consistent feedback loop between the database, cache, and queue, all in real time. And with a fan-out effect, because Twitter has a profile and follower ratio as well, those tweets that every single profile tweets to their followers is going to be curated to their home feed. And so in response to these demands, Twitter implemented its services into two primary ways. First, let's solve system loading. What they did in particular is that they associate posts with IDs and profile pages. And typically this would be just a randomized string that would have a specific ID called a UUID, which could be a profile string or any type of data piece that would connect a specific post to a user's profile and their followers as well. And first, posting a tweet adds to a collective pool of tweets. When someone requests to see their home timeline, the system fetches tweets from all followed accounts merged by timestamps and organized by timestamp. The simplicity of this operation is deceptive because the underlying relational database must perform efficiently to handle such large amounts of loads in real time. Second, Twitter manages cached versions of each user's home line. Where with the home line, they're able to manage out different means. Let me just move these really quick. And rewrite this. Apologies on this. User's timeline. And it's similar to a personalized mailbox filled with tweets, which is like a mailbox for tweets. Where this approach significantly reduces the load when reading the timeline because results are already pre-computed. So they're already saved with the user's own profile. So next time, for instance, if you don't have any Wi-Fi connection, you would already have a cached load saved from any social media platform, for instance, when you go log back on. And if, for instance, you are completely out of the network, you're not able to see new tweets or see new posts because you're not connected to their system. And so there is already a saved cache layer from each timestamp that you are on within their social media platform. And so when a tweet is posted, it's not just added to the public tweet collection, but also pushed to the home timeline cache of all followers, ensuring that they have immediate access to the new content. And this system design overall solves the problem of delivering a vast amount of tweets to a massive audience in real time. So if we were to go over the following image that we have, so in the case of the fan out effect, for instance, so we have a follower's timetable, and then we also have their IDs matched with every single post that they have. And so when a user posts a tweet, there's already a time series of timestamps already fanned out between each of the users that are interacting between each of the profiles that they have. And it's all meshed together between when a Twitter user is already having their following ID already associated with each tweet and their followers as well. So let me just zoom out to give you all of the following. I'll just move this. That's for our next example. And just get rid of that. Sorry about that. There we go. Now, to help solidify our concept understanding about system loading and scaling challenges, let's go over a concept example, for instance, when we are dealing with a city's mail delivery system, similar to how Twitter's load handling was already set in place. So the postal service, like Twitter's database, must process items at a central facility. So there's a central, let me just use a different color for this. And before distributing the mail to each individual home, which is like a user's profile, or their caches. The posting of each item is akin to sending out a batch of postcards to friends and family, specifically all across the city. So the post office sorts these cards and items to be delivered to them to the correct address. And with the correct address, the post office must ensure that all the postcards and delivery items are sorted and delivered quickly, just like as Twitter's system must handle the surge of tweets posted during peak hours without delays. If the city's postal service only had to deliver mail to a single neighborhood, it would be relatively easy, much like handling a small, consistent rate of tweet posts. However, in our city, people have friends and family in many neighborhoods, and each person receives mail from various contacts. This complexity mirrors Twitter's fan-out challenge, where tweets are not just sent to a few people, but potentially to thousands or even millions of followers. The Postal Service, therefore, establishes a system where postcards are pre-sorted based on recipient's address. And the Postal Service, therefore, focuses on ensuring that when the time comes to deliver the mail, each postcard can be sent out efficiently without overburdening the mail carriers. Just as Twitter's cache timelines allow users to access their feeds without existing or excessive loading times. Similar to Twitter's loading and distributing. Similar to Twitter's loading and distributing. There we go. And just to clarify our concept, every single data system must have a database, cache, and queue. There we go. So now let's go over a practice example to help solidify our understanding about system loading and scalability issues. So we are going to be focusing on a hospital database management system where we're creating a patient appointment system for healthcare providers. So let's design a data flow diagram for a healthcare provider's patient appointment system. The system must be efficient for managing bookings, cancellations, and rescheduling. So we need to ensure that there are accurate availability and also accurate information to minimize wait times. And we need to rely on following components. And every time that we have a data system, we need to have a database, cache, and queue. So we can use a relational database, cache layer, and a messaging queue for managing times, cancellations. Let's take care of this. Apologies for this. Messaging queue, here we go. And so overall, what we need to do, let me just zoom out of here. Is that the following steps that we need to create for our web-based interface for both patients and staff to manage appointments. We need to understand between how, one, the system's going to be responding for each of the following times when a patient is booking an appointment or canceling an appointment. And we also need to have notifications as well. Which can serve as a messaging queue. And steps that we need in order to be able to build out our system are going to be the following. One, we need to identify key components. Two, need to outline user interactions. Three, we need to detail our initial process. And that will be user actions. For user actions. For consider faults and failures. Where we also need to consider the hardware, software, and human errors as well. And finally, how do we optimize for real time and speed? And a lot of it has to do with the caching layer. And with our caching layer, it's going to be similar to how Twitter is actually already would be able to save the most recent cache with the user's profile with the latest tweet. So we would initially have something similar in the context of that. But these would be the 5 steps that we need to be able to build out our following patient data system that would be able to register users and to be able to either schedule them for appointments, cancel appointments, and reschedule appointments as well. So yes, this will be our first example for our practice problem. Now, let's look at a second scenario implementing a smart home automation system. So now we're going to be focusing on designing a data flow process for a smart home automation system that controls various devices like lights, thermostats, and security cameras. The system allows users to create automation rules remotely controlling devices. And receive real-time alerts. It consists of a following, and every time we have a data system, we need a database. Let me just clean that up. Database, cache, and queue. There we go. Let me just clean this part up. Every system needs a database, cache, and queue. And what we would need, namely, for our database, we can use cloud-based. Cache, we would use a cache layer. Queue, it's going to comprise of messaging queue. To be able to automate the different controls and rules. And so what we need to do to be able to develop this real-time database for storing user systems desire for settings and device states is that we need to at least figure out between just the different modalities of every single system that they have. Like this could be a series of Boolean functions that we could be able to create to have a certain system turn on and off depending on the given time and context when, for instance, we want a camera on or for night surveillance. And so what we need to do, similar as the first step, is that we need to identify key components. Second part is outline user interactions. Third part is to detail internal process. The fourth part, consider all faults and failures. Fifth part is then optimize for speed. So in the similar context for what we have from the first part is that for every single key component that we have, to go over them. So when we identify key components, we're essentially considering elements including their user interface and creating rules and controlling devices, the cloud-based system for automation logic, and the real-time database for device state and user settings, and along with the messaging queue that we would have to sync asynchronously between devices and the cloud service. Well, meanwhile, the user outline interaction allows users to set up a new automation rule like turning lights on and off during sunrise or sunsets via the mobile app, and the rules are already set in place. The third step would be having the cloud service process establish the rules and update the user's automation settings within their database and sending commands to relevant devices. While our consideration for all the failures and faults that may happen between the hardware, software, and humankind is that the system is already designed to handle partial outages, for instance, or when a message queue is temporarily down. There are commands which are queued until the service is restored, messaging the local device, putting all the queues in particular on the local device, so that way the cloud service is still being fixed within a fail-safe environment. And then optimization, we can use it for security, we can use it for speed, but really when we are creating a real-time database, we're focusing on speed and efficiency as well, to allow users to immediately create updates across the user interface and devices, ensuring all system components are synchronized in real time with the latest settings and states without the need for frequent polling. And the setup reduces network traffic. We need to reduce network traffic. So reduce network traffic and improve the responsiveness of the system to user commands and automation rules. And so let me just open this up right over here. And so yes, this was our second practice problem and example to be able to go over for system design, handling system loads and scalability issues as well. Thank you again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone. Today let's focus on the lesson for data models. So to be able to give a concept overview of what data models are, when creating software, one of the foundational decisions developers need to make is choosing the right data model. It is akin to an architect deciding on the blueprint for a building. The choice deeply influences not only the way the software operates, but also the problem-solving approach. Data models are the lenses through which we view and manage the complex reality represented within our system. So they are the lenses we see for our system. At its core, a data model structure, the way it is stored, accessed, and manipulated. It defines the rules by which data entities relate to each other. For application developers, this means translating the real-world entities into data structures and using APIs to interact with these structures. It's also about finding patterns in the chaos of the real world and fitting them into a logical structure framework within the software. So this is also applying to data structures. The choice of the data model is pivotal because it dictates everything from the performance characteristics to the types of queries and operations that can be efficiently performed. Whether it's a document stored, a relational database, or a graph model, each comes with its own set of capabilities and limitations. As data models layer one on top of each other, from high-level structures in an application down to the bytes on a disk or memory. Each layer for a data model offers a simple interface to structure data. And this layered approach is not just about the technical convenience, it reflects an understanding that different roles involved in building and maintaining a system need to interact with data at different levels of abstraction, meaning that it ensures that application developers, database engineers, and hardware technicians can work efficiently within their domains without needing to grasp the entire stack's intricacies. So this could be a wide variety of different data structures and algorithms that one could be able to apply when actually modeling data depending on the context of our given data that we are using. So even though the data models are considered extensive, they are really efficient when it comes to scalability, and some models are better suited to distribute different forms of data and better suited for different systems. They can influence development speed, such as space and time complexity, and there are more intuitive models which would have better trade-offs when it comes to storing data, or also the efficiency of what data model we would use. So, to provide context, we focus on efficiency for data storage. Let me move over here. Whoop. And access. So to be able to solidify our given concept, let's go over a concept example. So we're going to be focusing on content management system. To illustrate the importance of data models, content management system is a software used to manage digital content. A content management system developer might look at real-world articles, media, and user interactions and choose a data model that best represents these entities and their relationships. So we're ultimately using data models to represent real-world articles, video, and media as digital objects for data. And to go over the entities that are required in particular to be able to build a content management system, it's going to be the following steps. One, we need to figure out the entity representation. Second, the storage and retrieval of the media. The third and fourth are going to be, the third one's going to be focusing on queries and manipulation. And the fourth one is going to be focusing on hardware considerations. So let's go over each of the 4 steps, or 4 parts. So entity representation is going to represent each article, image, or video to be an object to be stored in a database, where that could be a relational database or document. Model. So we have a relational model. model or document model, where they will be stored in various objects. And to be able to go over the differences between relational and document model, let's put this over here. Relational here. Use a different color. Relational refers to, so relational model refers to data represented by rows and columns. A vivid example would be SQL. And meanwhile, a document model would represent objects stored on a document that could be any data types like strings, integers, or other data types. And a good example would be JSON or XML. So that's a bit of a side note for us on relational and document. And so then when we go over to storage and retrieval of media, once the objects are created, they need to be stored in a database. So objects must be stored in the database. And we could have a relational model where that would refine where it would involve around their tables and their relationships, while the document model might simply be about storing and indexing documents. And meanwhile, for queries and manipulation, the developer needs to consider how these objects will be accessed. So how will the objects be accessed? They will need to perform complex joins. So we need the relationships defined for them. So we need relationships defined for each object. And this is where a relational database actually excels over a document, because you can discern relationships between the two. And so the hardware considerations would also consider how these data models translate to the hardware level, understanding between what hardware is required. Are we doing, for instance, a document or relational model? And a key point I also need to bring up is that for their applications between relational model and document model, a relational model is great for, just gonna do this, great for structured data. And a document model is great for unstructured data. That's a key relationship between them. And so let me zoom out. There we go. Just need to expand upon this And so, yes, this would be the case for content management. And to be able to give an overview of our diagram of what we need to consider the full system, how it's going to be operating as a full stack application, and exactly what services that we're also going to be using in terms of front end and back end, just to give an overview, and its distribution as well. But this is just the overview for content management systems. Now let's go over a practice problem to help solidify our concept. So let's be focusing on a social media platform and then focusing on choosing the right data model. And this will just be an outline on how to make the decision for the right data model. In later lectures, we're going to be going over the different types of data models. So in the meantime, we're just going to be going over the overarching scope over what it takes for model selection and assessing specific data models to apply. But right now, we're just going to give an overarching concept overview. So the first step for us to be able to actually figure out what it means to be able to build a social media platform with the right data model, understanding which data structure would we need to use, is to understand the entity relationships. What is the data? And how do we put them in objects for object-oriented program? And the next part is to select the model to be able to match the objects. Let me just erase this. To give an example, we can have a relational versus data model. Next part is going to be implementation. Recognize all faults and potential failures. And also understand the relationship between the database, cache, and queue. So that way we know exactly what it means to communicate and update data in real time. To communicate and update data in real time. Next part is optimization. How do we make it better for speed and efficiency and storage? And storage. So speed, efficiency, and storage. Finally, evaluation. How well does the data model fit with real world implementation object creation storage retrieval and manipulation. So to be able to go over each of the following steps, just give them some extra space, is that within our social media platform, for instance, we already have data points that we need to take into consideration, such as a profile's user, or even actions that we need to consider how that data is going to be interacting with each other. Such as for Instagram, we would know about likes, followers, people to follow, and then posts to also be able to post within a given timeline, and how it will be curated within a different feed. So, for instance, in our given example, in Instagram, we have an action called tagging people. Now, we already know from our previous lecture that there are IDs already associated with every single profile that a person's going to be using. And then that profile is also meshed in with other profiles at the same time. So if a person were to instance, make a post on Instagram, that post is already associated with an ID from one profile, and it's already fanned out to multiple profiles, and it's already organized on the home feed as a series of timestamps. Organized by profile and timestamps like mail delivery. And so once we have already done that, we would then further understand between, okay, so when a person's already making a post or they're tagging a person, they are associating that data model of a post or a profile or a picture or a video, which are different intricacies of data which could be meshed in between one profile to a series of other profiles in the fan-out effect that we talked about in the previous lecture. And so what we need to do overall, just going over the steps, to be able to implement and create a data model is we need to understand the entity relationships. Just clean this up. What is the data? How do we put them into objects for object-oriented programming? And we will first assess the features requirements and understand the relationships between different pieces of content. And does the relationship data have a clear structure, or is it more free form? So, is the data structured or free form? In this example, it's relational. Model versus document model. And we're going to have a different lecture video come up talking about the differences between relational and document models as well. And in the second step, we need to talk about the model selection and then understanding the requirements. One might offer a graph data model in particular, for example, which is another form of the type of data structure as well, to make connections between different user profiles as well. Use a graph model. And then we figure out the implementation strategy. And remember, every single data system is always going to have a database, cache, and queue. And understand between the failures, the faults, which would eventually become failures, and have independent testing from the human, hardware, and software side to be able to actually implement our data model. Then the next part we would need to consider is optimizing, and we need to consider the volume of the content and frequency of searches. So we need to ask ourselves about scalability. And then finally, for the fifth step, we need to consider how well is this going to do in real world situations. So we need to ask, how well will the data model adjust in real world situations. And then we need to consider continual adaptation of the data model. And so yes, let me see if we can just fan this out and span it out a little bit more. And I'm also going to have the practice example problems also in the description at the same time. Let me just go over here. Yeah. Now, to cement the concept of data modeling, let's look at our second example of focusing on a practice problem for a multiplayer game. So this is also the reference article at the same time. I'm going to put it in the description below. But to give an understanding of exactly what it takes to be able to apply a data model specifically to a multiplayer game, we need to understand really just a whole scope between the features that require and are needed within a gaming platform where players can form alliances, compete, and trade virtual items. We need to keep track of these interactions and transactions in real time for a seamless gaming experience. So every single data system is going to require us to have a database, cache, and queue, keeping information all set up in real time. And the way that we're going to be able to build and scale our data system is going to be the following. One, we need to understand interactions. 2, choose a model. Choose a data model. The third part being real-time processing. Fourth being scalability. And the fifth part being testing and iteration. So going over these steps necessarily, to understand the interactions, we need to analyze player interactions, and unlike static content, these are dynamic. So we are dealing with dynamic data objects. So we could have a series of integers or counts depending on players' interactions of choice, depending on if they ever want to attack, kick, melee, or for instance, trade a certain item that is based within a list that we could have. So we're going to have multiple data structures within data structures as we are playing users' interactions within the game, since they're going to have different data types such as objects that they're going to interact with, or actions such as chatting between each other, that we would need to integrate different structures altogether. And then for choosing a model specifically for this, we're going to need a combination, as stated before, combination of data models to encompass full game experience. And then in the case of real-time processing, we need to create a data model that supports real-time processing with updates and such as in-memory game storage. Model must support real-time processing. And yes, that also means cache updates. Consistently. And the data model in of itself can also abide by Twitter's own model platform, where they are able to store caches locally, so that way a user's profile can also upload the previous data that was already stored. And in this case, we could see different transactions between different profiles and interactions between players. We can, for instance, apply a graph model to keep track of players properties, which can also refer to actions, inventory, etc. And when it comes to scalability, given the potential of a large number of concurrent players, scalability is going to be a priority. So we're going to need to design the data model to distribute loads across multiple servers. So we're going to have a data model distribute loads across multiple servers around the world. And finally, for testing and interaction, after implementing the models through testing and under real-world simulations. So we are considering all potential faults and failures in isolated testing environments 1 second. For hardware, software, and human. Paradigms. So all together, we will be able to create our multiplayer online game that is scalable across the world. So let me move this over and show you the full. And so over here. So this is our solution for a second practice problem that we would have in the case of our multiplayer online game. We will understand the interactions. Let me just clean this up. Choose the data model. Account for real-time processing, scalability, testing, and interaction. And iteration. And so, yeah, so this was data modeling and choosing data models altogether for this lesson. Thank you again for taking time to watch this. If you found this helpful, please, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello, everyone. Today, let's focus on a key concept in data models, really focusing on the types of data models. Two big important ones that we're going to talk about today are going to be relational and document models for the data models used in system design. So today we are discussing two predominant data models in the real world of databases: relational and document. So imagine a world where everything is categorized and placed in a box with a specific label. That's the essence of the relational model. And it was introduced by Edgar Codd in 1970. Where the model structure is about data and how do we organize it in tables. And a popular application for a relational database is Microsoft Access. There's also SQL as well. Just to name two. And this model structures data into tables, which is like a label box, each containing rows. Notice how each of them are in boxes and they're all containing rows, and they're all containing key components of data, even including tuples as well. It's overall a systematic approach that enforces a strict schema and is excellent for data with a regular structure. So. Despite skepticism about its efficiency and its inception, by the mid-1980s, relational database management systems with SQL as a query language became the standard. This model was ideal for business data processing, such as transactions and batch processing on mainframe computers between the 60s and 70s. So it's great for transactions. I'm actually going to highlight this part as well, use a different color. Let's see if I can highlight this. And fast forwarding 20 to 30 years later, and relational database management systems still command the field. And they power diverse applications from e-commerce to online publishing. However, no technology reigns unchallenged forever. The rise of NoSQL in 2010s marked a shift towards more flexible data storage. So, the NoSQL buzz originated from Twitter's hashtag capturing the growing frustration with the rigid structure of relational schemas and the desire for a model that could handle more dynamic data and larger scales more efficiently. This is where the concept of document models came into play. They focus on dynamic data. It was introduced in 2010s. In the 2010s, they handle unstructured data. And it was originating from Twitter's hashtags in order to be able to help capture the growing frustration with the rigid structure of relational schemas and the desire for a model that could handle more dynamic data and larger scales more efficiently. Here, the document model, just to give an example, relaxes the strict schema of relational databases, and the data is stored specifically in self-contained documents such as JSON or XML. So JSON for documents and XML for relational. Databases are here, and then document. Coinciding over here. And that's also including NoSQL. NoSQL meaning no structured, rigid databases, and focuses on unstructured. So relational focuses on structured, unstructured. And so therefore, this is just the brief concept overview between relational and document models. Let me just clean some of this up for you folks. Dynamic data, relational model. There we go. So let me just move this over a little bit. There we go. So this is just dealing with relational models and document models. Now, to be able to cement the idea of the concept between relational and document databases and models, let's go over a vivid example between two real-world examples focusing on LinkedIn as a relational database, a relational model, and then a law school application that is using JSON data to be able to use a document model to structure out different forms of data. So on LinkedIn, just to give an instance of this, I will just put in right here. Let me just take care of that. There we go. Relational model LinkedIn.
slash resume, because you're going to have a person, and then you're also going to have their title, experience, and also career and education too, as just a number of fields. For this can all be formulated within the structure, and therefore that data model can also be applied to other avenues at the same time, depending on how you want to encapsulate each object that you are already programming. And this is also branching off of object-oriented programming as well, just for further context. And meanwhile, for the law school app, for a document model, for what we are seeing over here, this is a JSON document, really, just with a number of fields and different means of data in of itself. What it's doing is that this is actually a law school test app that I'm doing as a side project right now. And each field it's going to have a series of questions, question choices, and it's probably going to have some type of passage that we have for each question, because this is unstructured data that we are dealing with, since it is we are also dealing with different types of tests as well. Type of tests, because the LSAT has 4 sections as well. And plus, choices are saved as well. Choices are saved locally as a cache on the user's phone. That way they can take the test without the need for Wi-Fi. And so that would just be an example, really, for JSON data. I'm going to see if I can zoom in here. It's just a lot of text that we're dealing with. So there we go. That's better. So this JSON document that we have is going to have a test number, the test type, the time required, directions, questions as well. And each series of questions is an array inside of an array where we are going to have a given prompt, and we're going to have choices as well with the correct answer and explanation. Then we're also going to refer that for each of the following passages that we have accordingly, and then treat this organized form of data into an unstructured document, so that way the choices can be saved dynamically, since users probably want to take a test, maybe restart a test at the same time, and all that data can actually be restructured and manipulated in real time. So these are just 2 examples that we have for a resume, and then also a law school application that we are making. Let me just move this over. There we go. So now let's go over a vivid practice example, practice problem, to be able to understand the scope of a relational database and how to carry it about. So let's consider this type of data and its structure. If the data is highly structured and interconnected with clear one-to-many relationships, like employee to their job positions, then we will apply a relational model in this case, since we are dealing with employees, positions, I could say education, or seniority. We would apply a relational model. To structure our data. And the question is if we can automate our structure unanimously across the board, it's going to be relational model. In order to actually assess what data model we would use, a relational model versus document model, there's really three components that we need to consider in order to do so. So they would be: one, assess the data structure. Two, evaluate the query pattern. And finally, consider the application's flexible needs. Flexible needs when we apply it into the real world. When we are assessing the data structure, what we need to consider the type of data and structure. If the data is highly structured and interconnected with clear one-to-many relationships, like employee to their job position, the relational model will seem appropriate. And in this model, each employee has a unique identifier and tables for job position. So if we have, for instance, if we have a unique identifier and table we can bring, we'll do a relational. Just think of it as if we can make a table out of this. If not, then we're going to have to go with the document model. And the table can be used for job positions and education. Be used for example, job positions and education. Now, to evaluate the query pattern, we need to reflect on how often and in what way the data will be accessed. If you need to perform complex transactions or queries that involve multiple tables and relationships, so if we need to do multiple queries for multiple tables, we'll do a relational model. Relational model. And we need to figure out for relational models have data consistency, and it's all structured from the beginning. And finally, when we consider the application's flexible needs, we need to ask ourselves if the application requires schema flexibility. If you need the ability to quickly adapt to changing data structures, such as new fields without database migration, the document model would be actually beneficial. But since we are dealing with structured data, structured data, and not much change. And not much change is occurring, we do a relational. And another thing that we also need to point, I apologize for not including this yet, but this is the last one. We also need to consider the scalability and performance. Consider scalability and performance. And we need to consider volume. Volume of data. Faults and potential failures. The data model in of itself, when it comes to relational databases, would typically rely on something that is already structured and already established and already knows exactly the protocols between how to handle such errors and how to scale with larger volumes. So with knowing exactly between the differences between relational and document models will be our next practice problem. But in the context of relational models, in terms of scale, relational models don't seem to be, they don't perform better compared to document models because document models deal with unstructured data and can abide by the flexibility and such. But of course, you can interchange between relational and document models, but you have to understand the context of the problem they're actually dealing with to begin. So moving out from this. So yes, in order to implement our structure, we also need to understand, can we make a table out of this? Is it going to be consistent data? Will nothing really change that much? We need to assess the data structure, evaluate the query pattern, and consider application's flexible needs. If there's greater flexibility needed, we'll use the document model. If it's already structured, we'll use a relational model. And then we will have to consider the scalability and performance as well. So let me just move out even further. Actually, I'll just move this. 1 second. There we go. So this is practice example 1. Now let's focus on the document model side over the relational model. So we're going to deal with our example within a content management system. Now a content management system is a data system that is really, as the name suggests, focuses on content. So we're going to have different data dealing with different data where it could also obtain and abide by articles, video, images, and other media. And with the document model, the data is unstructured. With the data in itself unstructured, that means it's going to be dynamically increasing, so we can add on new forms of data throughout the entire content management system. So it's always being dynamically added and ever expanding. A good example is NoSQL. And I'm just putting up the Wall Street Journal as like one example as content management system, because you're dealing with articles, for instance, images and video, and forms of unstructured data that need to be ever expanding as well, because every day there's going to be some news. So for a content management system, we're dealing with a dynamic website, as the name suggests, at the same time with multimedia elements. And the elements for us to consider applying a data model are going to be the following. One, we always need to assess the data structure. Two, evaluate the query pattern. Consider applications, flexibility needs, and assess scalability and performance. Now, these parts are going to be focusing on the document model as a whole. So the way how we assess the data structure to decide on a document model is that our data is less structured, no table can be applied, it's ever expanding. It's ever expanding with different forms of data / content on a consistent / daily basis. The document model could be a better fit here, which allows for each article to be encapsulated by its authors, media, and other categories to fit inside of a single document, since, for instance, an author may include a video or a couple images to be able to explain the point. And so in order for us to evaluate the query pattern, we need to consider a content management system fetching complete articles along with the associated data display. So fetching articles and its associated media, display, and cache layer. Like, for instance, video. Like, that's a good one. The document model's benefits, it's also beneficial locally. Like a YouTube video, for instance. For example, like you can have it play locally even if you're not connected whatsoever. And the document model's locality benefits means that fetching the data with a single query, and it simplifies the data retrieval and reduce server load. Okay, so we reduce the server load. and simple query. Extraction. We'll have to consider the application's flexible needs. Dynamic, flexible needs. The data is ever expanding. Because the content management system needs to adapt to varying content types and structures, the documents model schema's less approach allows one to introduce new content types and modify existing ones, and it overall impacts the database's schema, offers flexibility and speed. And finally, we need to assess scalability and performance. In a content management system, especially those with high traffic that require efficient data retrieval, high traffic requires efficient data retrieval in real time. And the document stores offer faster reads by storing related data together and can handle high throughput associated with web content delivery, making them ideal for the scenario. So, easy retrieval. And faster reads and handles high throughput of content delivery. Much like in the case of uploading a YouTube video. Because every time you upload a YouTube video, it's for every single data system, we need a database, cache and queue. While the YouTube video is actually being uploaded in of itself, there are moments where there's elements of locality as well to be able to have the video already be uploading at certain key points, and also if one is searching a video in real time, they're able to have the video also come down and load simultaneously at small chunks and tidbits, also depending on the definition and quality of the video as well. So in of itself, YouTube uses a document model type of data system because of the amount of content that's also required. And that's also applied, for example, the Wall Street Journal with articles, videos, and such. So let me just move all these entity steps to the side. There we go. All right, there we go. So yes, so in our document model, what we're doing is that we're dealing with different modes of data. The document model is great for unstructured data. For the data itself is dynamically added, and all of our 4 points that we already have is that we need to assess the data structure first, evaluate the query pattern, consider application's flexibility needs, and assess scalability and performance. For in the first part, while assessing the data structure, our data is already considered less structured since one, we're dealing with different forms of data such as articles, videos, and images and content, and no table can be applied. The system that we are applying it to is ever expanding and requires fast retrieval as well. We need to evaluate the query pattern, like how well it will be efficient if we have different forms of media. For instance, that could be very high amounts of gigabytes of storage. We need to fetch articles and its associated media display and cache layers, like for instance the video. And it's beneficial locally because one could have parts of media already stored locally to the user in simplified query processes. And it's a simple query extraction to be able to get that specific form of media. And we have to consider applications flexibility needs. If the content is ever expanding, has higher traffic, then document model will be well assessed. And assessing scalability and performance, we already have, for instance, high traffic requirements, and we have efficient data retrieval in real time, so the caches is completely updating. And we have easy retrieval and faster needs in handling a high throughput of content delivery, like uploading a video on YouTube or searching for it as well between the database, caches, and queues. And so, yes, this was a video lecture series video of data models focusing on document models and relational models as well, and vice versa, relational models and document models. Thank you again for taking time to watch this. If you found this helpful, be sure to like and subscribe, and feel free to. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to be going over the system design concept of relationships with databases, not to be confused with relational databases. We're just going to be focusing on the intricacies between object-oriented programming and how to develop the key relationships with databases. So, to be able to have us get started with the following concept, we have to understand the complex nature of relationships within a database, and they can often be dictated by choices between either choosing a relational or document database. Document. And when considering a relational database, one of the fundamental concepts to grasp is that of normalization. Which is a process designed to minimize redundancy and avoid undesirable dependencies. So we minimize redundancy, such as if we already know exactly what specifically to be able to get for a specific profile that is designed within a domain, we're able to actually be able to build up a profile, for instance, based on job, title, education, career, and we already have those key data points that can always be inputted from the user side all the way to a database. And this concept is tied closely to the management of many-to-one and many-to-many relationships, which are omnipresent in relational databases. Normalization leverages the use of unique identifiers. Unique identifiers, which are really just complex strings that are already stored inside of a database to keep track of a user's profile. It's typically a random generated string, so that way that ID is already associated with one's content in particular. And if they want to be able to pull from a specific database, they already have that ID associated with that amount of data to be able to pull down. And a method to ensure consistency, redundancy, and ambiguity is to understand exactly how that ID is actually going to be associated with in the given context of the domain, and also the application one is also developing. To give an example, for instance, instead of storing the quote-unquote greater Seattle area directly in every record, we can just store a region ID that refers to a single entry in a regions table. So we can just put in because we already know exactly what we are asking where specifically the location is, and then we can update with other fields as well, such as title, job, education, and such. And these normalized unique IDs also serve another purpose. They form the basis of a join operation. Let me just move down here to explain what a join operation is. Which a operation in relational databases to allow combinations of data to be pulled from a database. A good example I can give is a profile name and picture. And in relational databases, IDs are very beneficial to be able to pull certain aspects of data. However, sometimes people will trade off between the relational database and the document model, largely to either have the question about flexibility and also expanding upon different forms of data and also the application needs as well. So let me just pull this out. Now, to be able to solidify your understanding about relationships and different databases, let's go over a concept example to help solidify. So let's consider professional networking platforms such as LinkedIn, where users can add their work, experience, education, and positions, and various backgrounds as well. In a relational database, a user's work history might be stored in a positions table. We can store information in a table. And meanwhile, document databases the relationships become embedded with the user's profile. So relationships become embedded with a user's profile. And this can not just only expand between social media platforms like Twitter, but can also apply to Instagram, Facebook, and other social media platforms that abide by a dynamic approach / ever expanding data. Ever expanding data. However, a document-based model would actually face some issues, namely if there was a company rebranding such as Twitter all the way to X. If there was every single post associated with the name Twitter on it, it has to be updated with X. So yes, just a quick concept example overview. So to be able to solidify our concept understanding, let's go over a practice problem to be able to further understand how we apply relationships between different databases, between
relational versus document model. So in this example, we're going to be focusing on a resume builder, and we're going to be creating a professional social network platform which stores user profiles, including past job experiences and education. The company now wants to include a feature where users can add professional skills and recommendations, much like in the skills section of LinkedIn. So, of LinkedIn example. And so what we will be doing in this case is that we're just going to be going over the following steps. This is just going to be a brief overview, very simple process on what to do. So step one, we're going to have to define entity relationships. Can we put the info in a table, information in a table? With the second part also focusing on determine the types of relationships. Will an ID be needed to filter out the data? These are the three questions that is just a question that we just need to ask ourselves. And then we obviously need to do the next part, which is implement the relationship. And since we have the same social network, let me just move this really quick, apologies. And since we are focusing on a social network, in this dynamic where we have a user ID, it looks like it, just based on this one figure that we have for one of the many relationships. We can even put a tree structure at the same time, depending on job, experience, and education as well. Even the specific ones that we would have all pertain to the user. This is the data model that we use. We use a tree model. Let me use a different color. Words associated based on a user's ID, which could be a randomized generalized string, which would be a UUID. And then that UUID is also related with the positions, education, job, and then also a different series of educations as well. They would even specify between the different skills that one wants to also put, depending on the user's ID that is already set in place. So what we would do for relational databases, we create separate tables. We create separate tables. Associated with users' profiles. And so this is just an example of what we do for a resume builder where we apply a relational database. Let me just move this out and clean this up for you folks so you see exactly what I'm talking about. Clean this up. So this is tree model. This is the skills that we would section we would put in for a resume building profile, and then we have to ask ourselves based on the criteria on we need to determine the types of relationships and will an ID be needed to filter out the data. So that way we can know the difference between applying what type of database we need to put in. Do we need to put a relational or document model? Asking model / database. For every single data system is always going to need a database, cache, and queue. And we have to also consider the faults and failures. Always consider the faults and failures. Here we go. And so, yes, this is just our first practice problem that we have. Now, to go over a second practice problem to be able to help solidify our conceptual understanding between how to apply different forms of relationships depending on exactly what database model we actually want to put in, we're going to do the same type of concept, except we're going to be focusing on the job section for our resume builder. And what we need to really do, as usual, we need to ask ourselves exactly, we need to, one, define the entity relationships. And the second being implementing. And so, the relationships. For the first part, we need to define exactly what are the original entities, and are we adding entities to particularly the job, its description, and also the title of it. New entities are going to have their own profile associated. So we need to always ask ourselves, will an ID be needed? If so, yes, relational. If not, then document. And is there, no, hang on. And we also need to ask ourselves about redundancy. Is it there? Let's just move here. Is it? Redundancy, is it there? And if it is, we go relationship. If not, we go document, and then we implement the relationship accordingly. So with relational databases, we implement a table, and then for a document model, we're going to implement as it's stated. For a document with ever expanding data and change. So yes, so this is our second practice problem in terms of understanding between relationships and different forms of databases. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone. Today we'll be going over the system design course. Today we'll be focusing on the historical context of relational and document models and databases. So to be able to give a breakdown, we are going to be diving into the annals of database history, where we encounter a long-standing debate between the differences of relational versus document. For when we are exploring the context between different databases, relational versus document databases stand out between each other because the relational model has solidified with SQL and was very revolutionary against another debate in the 1970s. So relational databases
solidified an earlier debate in the 1970s because data could be organized into tables. And we typically, a good database would be SQL. I'll just put an example over here. So with the concept of how data could be organized into tables with rows and columns, we're able to actually understand more about how our data can be orchestrated. For in the 1970s, there was a committee called the Conference on Data System Languages, also known as CODA-SEAL, and implemented by several different database vendors. They also had their own model called the CODA-SIL model. The CODA-SIL model was a generalization of the hierarchical model. It was considered a tree structure with parents and nodes where the nodes represented records. In the network model, a record, however, there was a secondary one, model, was also known as the network. Model, a record could have multiple parents. Could have multiple parents. For example, there would be one record. Network model could also be another example of the greater Seattle area. And then the greater Seattle area would be the parent, and then the nodes would equal different addresses. And every user who lived in that region will be linked to it. And this allowed many-to-one and many-to-many relationships to be molded. Allowed many one-to-one and many-to-many relationships to be molded. And a query with CODA-SIL was performed by moving a cursor through the database by iterating over lists of records and following access paths. If a record had multiple parents, multiple pointers, a record with multiple parents the application code must keep track of every relationship. And as you can tell, this would actually lead to very complex computational problems if you're keeping track of every single relationship instead of organizing the data accordingly. For even codicil committee members admitted that this was like navigating around a n-dimensional data space, meaning that complexity would constantly increase over time. So time, complexity would increase over time in n dimensions. An n-dimension data space. And to clarify what n-dimension is, it's also referring to big O notation as well. For the more complex, for instance, a software or algorithm is already set up in place and has to go through n number of iterations, the greater the computational time and complexity. And so there will be a video in the future about big O notation, but right now, the point of it, just to communicate it, is that codicil models, and especially the network model, since it had to keep track of every single relationship, was considered complex by nature, and there had to be a better alternative, and this is where the relational model would eventually come to play. So let me just go over to this picture. This in of itself would be considered the network model that we have over here. Notice the parent, that we also have to keep track of every single relationship that we have, and each parent would also be considered for every record that we are already inserting in. And then this is also the relational model, and this is just the document model, but I'm going to be going further in depth onto them. So the relational model laid out the data in the table as specified before by rows and columns, and there was no nesting of structured data. We can take a look at the picture over here. For we notice in particular there's always associated with an ID, and that ID is already associated with the customer name, status, and you're able to extrapolate just based on one parent. So in of itself, it's kind of like taking the network model and putting it inside of a table, so you could be able to have tuples or rows and columns as well to indicate that one specific ID, therefore making it more efficient and less computationally expensive. Let's put this right here for reference. More efficient. And less computationally expensive. And one could actually read any or all the rows of the tables, selecting those that would match with an arbitrary condition. And one can read a particular row by designating some columns as a key and matching them with a pair. So one could be able to figure out between the rows and tables. And this is also going in line with data structures and algorithms, where one could apply a map or a tree to be able to actually search through the database that they have. In relational databases, the query is optimized. Queries in relational databases are optimized and provide access paths for specific data inquiries. Meanwhile, when we're going over the document model, I'm just going to use a different color. We'll just stick with okay. In the document model, a vivid example would be JSON, where we're able to have nested records and allow easier retrieval of specific components within the document and allows expansion of unstructured data. Like for instance, if we were to go up, I'm just going to go over to the document model example. So this is a document model for an HTML file. So an HTML file is going to be having a backbone between a head, title, and other headings, and also paragraphs. So one would be able to implement and ever expand between their HTML file. An HTML file is basically just the skeleton of a web page. And people can customize their websites any way they like with custom titles, the amount of paragraphs, etc., and then also apply with their CSS for styling and JavaScript for functionality. Let me just expand upon these to make this bigger. There we go. HTML document, example of a document model, which is a skeleton of a web page. That's what an HTML is. People can customize. So I'm just going to make this red. Go. All right, let me see if I can further expand this as well. Okay. And so, yes, this is the historical context for relational and document models, even in the context between the history that was already present with developing document models by going back on the codicil model, and also understanding the nature between its hierarchy as specified in the image over here, and then also the differences between the relational model and then also the document model as well. And I will have the notes already in the description for folks to be able to download out of their own time as well. So yes. Now, to solidify our concept, let's go over an example. So let's focus on imagining a simple application for managing a library, inventory, and patrons. So we have a library and we are managing an inventory of books and patrons. In the relational database, we will see patrons, books, checked in and out, all organized in a table with their respected IDs. And can have multiple tables depending on domain and context. So if we were to consider a document-based database, each document could have details of their checked out book, such as, for instance, if I were to go over, like, let's just say that this is a JSON data, so we can have a book title. We'll just call it The Lamb, and this is a string. Then we could have checked in like August 13, 2023, and checked out at August 20th, 2023. And that could be a string as well. Always remember your data types, depending on like exactly what you need in particular, and they're always separated by commas to be able to start, and then we'll have our semicolon here. So that could actually serve as a document model for our database, and each patron's document could include their loan book and personal information appearing conveniently at first glance. However, We have to consider the changes in book information, such as new edition, author details, consistent updates, though. 1 second. Consider consistent updates, but with flexibility of dynamic, ever-expanding data. So yes, this is just our concept example. There we go. Here we go. Let's put this as an example JSON. There we go. And so, yes, this is our concept example for a library and managing books and patrons for relational and document models. So to be able to solidify our understanding for our concept, let's go over a practice problem. So we are tasked with implementing a feature for a new book club with a library application. So we're focusing on a feature for a book club library application. Where users can have many-to-many relationships with books. Users can have many-to-many relationships with books, meaning desires such as genre, author, or publication dates, just to name a few. So what we need to do is that one book can be favored by many users and one user can favor many books. One book can be favored by many users and one user can favor many books. And for us to be able to develop the schema in order to solve this problem is that the first thing that we need to do, let me just use a different color. One, we need to identify the relationships with the data and users, and then also you need to implement the correct database. So in the first step, we need to discern if the data can be organized in a structured format. If so, then we go relational. If not, document. And once we have decided exactly based on the context within our domain over what we need to put in for the database, we are going to see if we can actually organize our data. Well, since we only have a book that we are organizing based on users, and those users and books can be associated with each other, we can build a table as a result, such as, for instance, we can do well, you can put an ID for a specific user. We'll have the user's name, the book title, genre, and then etc. And yes, we can make a viable table out of this. So yes, they can all have different cells and rows and columns. Since we have many-to-many relationships, that's the key. Many-to-many relationships. It's also structured data. We know what goes in and what comes out. We already know that we'll have a user, their name, their book title, and genre, and that can actually be associated as well. So we will be implement a relational database based on context and domain for our given problem. So what we need to do is that in this example, we need to create a table called favorites to handle the many-to-many relationships. This table would have IDs and foreign keys that also pertain to the user's name, the book title, and their genre at the same time, to enable a simple and efficient way to manage the relationships. Create a simple and efficient way to manage relationships. Since we deal with many to many, since we are dealing with many to many relationships with data. And so yes, let me just see if I can expand upon this. And I am going to have screenshots already labeled and given to you folks, and links in the description that will be downloadable, so you can download the notes for your reference as well, along with the practice example that would also be coinciding with each of the videos that we were making. So yes, that'll be over here. Now, for us to be able to solidify our concept understanding with the historical application of different forms of databases, we are now going to be continuing our example of libraries by focusing on a library book inventory. Now, the library wants to add a feature for tracking multi-genre categorization for books. So, the library wants to add feature tracking for multi-genre categorization for books. Each book can belong to multiple genres. Each book can apply and belong to multiple genres, and each genre can encompass many books. So we already know, just based on what they were requiring, we have a book, or any book, apply to multiple genres, or each genre to many books. It looks like that we have a many to many relationship. Here. Sorry about that, just have to clean that up for that bug. And then what this already signals to us is that we still need to abide by our following steps. Is that one, we need to identify the relationship type, which we already done up here. And then the latter part, there we go. Implement the correct database. So when we've already identified many to many, that's already signaling to us we need to decide the proper database, relational versus document. And it looks like many to many refers to relational because it's structured, organized. Let's go over here. It's structured, organized, and can create multiple and unique IDs. IDs. There we go. And then we implement the correct database, which we already know is going to be the relational database. So similar to the book club feature, we can have the same type of table that we have. So we can have an ID, we can have a book title, book genre, and this table can refer to book genres. Refer to book genres. And then we can apply multiple categories. So let me just put this up. Can apply to multiple categories for our relational database. And so this is just our second example of what we would do within adding in our library book inventory. Let me just move these choices up so that way you folks can actually see all together. And I'm going to need to move this. There we go. Actually, there we go. I'll just zoom out as much as I can. And then, all right, well, never mind, I gotta do this. Refer to point number 1. And just zoom in for you folks. There we go. And so, yeah, this was the historical context between relational and document databases, and given the full encompassing scope and thinking through how to apply the correct database depending on the context and domain that we are dealing with. So yes, thank you very much for taking time to watch this. If you found this helpful, be sure to like and subscribe, and feel free to. And if you have any other questions, please feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we'll be going over the concept of data locality in our system design course. And so to be able to help us get a deeper understanding about data locality and what it means, when we talk about data locality for queries and databases, we're referring to how data is organized and stored to optimize access. Over here, how data is stored to optimize access. Imagine a library where all pages of a single book are scattered across different sections. Every time you want a particular chapter, you have to search the entire library. This is akin to data being split across multiple tables in a database. However, if the entire book is in one section, you save time. This is the essence of storage locality in document databases, where documents are stored as a single continuous string in formats like JSON, XML, or BISON. Or BSON, sorry. So, document, databases,
single or set of strings in document. Such as JSON, XML, or BSON over here. And so for our given example, I'm just going to zoom in. We have a JSON file that we have. We notice that we have the strings that are already set up in place, and they are organized accordingly, and this is for an LSAT application. So this is a JSON file to be able to start with. And the advantage of this approach is significant when your application frequently requires access to the whole document, like rendering on a web page. Here, having all data in one particular place means fewer index lookups and disk seeks, leading to faster performance. Yet, there is a caveat. This is only beneficial if you need large portions of data simultaneously. Only beneficial needing to see large portions of data simultaneously. Databases usually load the entire document if only a small part is needed, which can be inefficient for large documents since the database is not the data is within the database and you're taking a device and you're connecting to the database. However, with data locality and with document-based models, the data is stored locally on the device you're using. So, in of itself, when you have an app that you already download on the App Store, and it has documents already associated with it as a document-based database model, those documents are also downloaded on the app, so it's all local, and you're able to have faster lookup times since the data is already right there. Moreover, there is a bit of a tricky situation when it comes to document databases. Updates can be tricky. If a document size changes due to an update, the whole document needs to be written. So if you want to add a particular field, you're going to have to spend a lot of time, in particular, getting through this entire JSON file to be able to update every single component so the data is showing inside of the application or any other piece of software that you're actually using. The whole document Hence, the best practice is to keep documents small and avoid size increasing updates to leverage storage locality efficiently. The notion of data locality isn't confined to document databases. Relational databases have begun to adopt similar concepts, allowing for schema designs that nest related data closely together to gain similar advantages in data retrieval efficiency. Convergence of these models, both relational and document, is the industry's response to varying data storage and retrieval needs. Relational databases have started incorporating features to handle XML and JSON, blurring the lines between them and document databases. Meanwhile, relational databases have been incorporating components of document-based models. I'm just going to put in such as handling features of XML and JSON. Meanwhile, document databases have introduced capabilities for relational-like operation, like joins. Document models implement
relational database components. Components. This convergence benefits applications, allowing them to choose the optimal feature set from both worlds, depending on their specific requirements. A hybrid approach, I'm just going to put in the definition right here. A hybrid approach combines the strengths of both relational and document models, appears to be a promising path for future database technology. A hybrid approach combines both components of relational and document database models. Hybrid approaches provide flexibility and performance optimization for a wide array of applications, ensuring that the storage model can be tailored to the specific needs of the data and how it's accessed. So, hybrid provides performance and flexibility of data retrieval and processes. So if we want to go over our notes, namely, let's clean some parts of this up. Components of document-based models. Okay, so relational and database and document databases. I'm just going to clean this part up so we already know what we're talking about. Document databases. So this is called the hybrid approach in our given example, such as put in the joins example that we talked about from document-based models right over here, ex joins, and public and private over here, our JSON file. I'm also going to be, let me just underline this part. There we go. And so, yes, this is our concept of data locality. Let's move over to a concept example. So to be able to go over our concept example of data locality, let's look at an example of a blogging platform. And in this blogging platform, we are considering where each blog's post is a document. Each blog's post is a document. Users can read, write, and update posts, and if the platform uses a document database, each post might be stored as a JSON object. Each post will be stored as a JSON object. We're doing a document database, which includes the title, content, author, and comments. When a user opens a blog post, the system retrieves the JSON object. Because of storage locality, the system fetches all the information in one go. fetches all information in one go. Therefore resulting in a swift display on the user's web page. Now imagine that the platform includes a feature allowing users to add images within the post. Feature example. Add images to the post. If these images are small and embedded directly in the JSON file, it aligns well with the recommended practice of keeping documents small. But suppose a user adds a very high resolution image that significantly increases the document size. In that case, the performance advantage of storage locality can be diminished, as updating the document now requires rewriting much larger files. So when we add images to the post, make sure the images are small, easy enough for the JSON file to handle, easy enough for the JSON file to handle. If too big, need to rewrite the whole JSON file. If the blogging platform were to move to a hybrid model, the text content of the blog could be stored in a document database for quick retrieval, while metadata, authors, and comments could be stored in a relational database, allowing for more complex queries and relationships. So let me put in hybrid model, basically best of both worlds. Use quick retrieval of document use quick retrieval of document databases while storing larger files in relational databases. Therefore, creating an ever-expanding dynamic-based data-intensive system to scale with large amounts of data. And so yes, here's our concept. There we go. Let me just move this over here. And so yes, this is our concept example for creating a blogging platform that can handle large amounts of data. And we also focus on the concept of document models and relational models and how to create a hybrid model as well from a conceptual overstand view. Now, to be able to solidify our concept, let's go over a practice problem. Consider an online bookstore application, and the system must manage a large inventory of books, customer orders, and reviews. And for any data-intensive system that we have, it's always going to need a database, cache, and queue. A document database is used to store details about books and reviews. So a document database stores details of books and reviews. And meanwhile, a relational database manages customer and order information. Manages customer and order information. So a cache is employed for quick access to book data. A cache used for quick access of book data. And a message queue handles the stream of incoming orders. So the queue manages the stream of incoming orders. And what we need to do is to be able to showcase the workflow for actually understanding the interaction with getting the book details in the document database, understanding how to get the customer data in the relational database, and the other processing through the messaging queue. Additionally, we need to consider failure points to highlight any faults that may lead to failures from the hardware, software, and human side as well, such as a database going offline, and how will the system maintain consistency and recovery over the events. So to be able to give an overview, we're just going to go over 3 different steps or 3 different entities to be able to go through. 1, we always need to identify the key relationships. And as highlighted already before, we have a database cache and queue. And with the database cache and queue and how they're all managing to work together, let's list out all of the following components that we have. So we have a document database, relational database, cache, and queue. Since these 2 are technically the databases that we have up here. And to understand how each of them actually work altogether, we need to understand the relationship for how, since we have two different forms of databases, how are they going to match up? Well, to give the overview, the document database must be queried to retrieve book details, since we already know it stores the details of books and reviews. So if it's going to be stored, that means we're going to have to put queries to get book details and reviews. And that means we need to actually update consistently with the cache to have the information already there and present. And that information, since it's already there and present, the document database is going to store that information in the cache. So book details are stored here for quick retrieval. Because in document databases, since we are given a set of strings that we already have within our document, and it's beneficial to be able to have all the information there and present within our application, it makes sense to be able to have the data already present on the queue for quicker lookup times. And then meanwhile, the relational database is queried for customer data and order information. So queried for customer. Let me just get rid of this part. I just needed it for a bit of a placeholder. For customer, let me just move this over here. And use a different color as well. Queried for customer data and order information. And since a queue manages the stream of incoming orders, the relational database is also coinciding with the queue. For the queue manages the order processing via a message queue. And step 2, illustrate the data system. And to give that overview, namely, what would happen is that you'd start with customer first, placing the order. The system querying the document database for the book details. Checks the cache. Then retrieve the customer data. From the relational database. And finally, process the order via the messaging queue. Let's just underline that red. Also cache, so we already know, because every data intensive system is always going to have a database, cache, and queue. Over here. And then finally, for our third step, we always need to figure out how to handle faults and failures. Handle faults and failures. And so within our workflow that we already have to handle the faults and failures, we can just go through the entire walkthrough that we already have, and we can pinpoint different faults that may occur from a hardware, software, and human standpoint. So looking from a hardware, software, and human standpoint. We're going to go through our workflow diagram. See the faults. From each step to mitigate failures. And implement protocols. Implement recovery protocols for each step. And yes, from all three of the via hardware, software, and human side. So again, we would just pinpoint different faults and failures that we'd have. I'll just use a different color over here to illustrate the point. So we could have see the faults, see the faults, see the faults, see the faults, see potential faults, to mitigate failures, from hardware, software, and human side. Let me just go up and scroll up to see if we have it. Let me just move this over here for you folks. That way you could be able to take a screenshot of these notes, making it more efficient. Let's move the third one over here. There we go. That's better. Just gonna clean up these notes over here. That way you would be able to there we go. So yes, going over the whole system. This is just the practice problem 1 walkthrough. Now, to be able to further solidify it, let's look at our second practice problem. So in this one, we're going to be building a corporate management system. So namely what we need to do in this one, imagine that the corporate management system handles registration schedules and participant feedback. What we will be using is that we will be using a document database. Oh, sorry. Relational database. Since we are creating a hybrid, data system, and also every data system is going to need the following: a database, cache, and queue. So in our document database, we're going to be using a NoSQL. Which is best suited for flexible data storage of event details and participant feedback. And meanwhile, the relational database maintains registration and scheduling. Maintains registration and scheduling. Meanwhile, the NoSQL event details and participant feedback. Meanwhile, the caching system that we will need provides instant access to the scheduled data, and the messaging queue is in place for processing feedback and updates. Back and updates for the messaging queue. Well, meanwhile, the cache instant access to scheduled data. And yes, that cache is going to get that information from NoSQL. NoSQL database. Meanwhile, what we need to do within our given problem is that we need to develop a scenario where a new feature allows participants to sign up for event updates. So that means a new feature allow participants to sign up for event updates. And we need to configure and work through the data flow and interactions to implement the feature. And we need to consider how registrations are tracked, schedules are updated in the database, along with the cache system reflecting these changes, while addressing what happens if an update process is interrupted and how the system handles particular failures to avoid miscommunications or data inconsistencies. So that means what we need to do, namely, it's much like identifying, like, once we already build out this new feature, how is it going to fit within the new database and the whole data system. So what we need to do first, as usual, is identify key components, and relationships. So namely, every data system is always going to have their database, cache, and queue. So we have a hybrid database with a document and a relational. Well, and then also we need to figure out how the relationship matches up the cache and the queue. So going back from our previous example, we already know that the document's always going to be related with the cache, and meanwhile the relational is always going to be related with the queue. Since document, as stated before, already focuses on event details and participant feedback, while relational databases maintain registration and scheduling. So going over here, document. Well, to break down the following feature, what we need to do is that since we are focusing on participants, we will have participant feedback. As stated over here, yeah. Well, the relational database focuses on scheduling. The cache showcases access to schedule, and then the queue always processes updates for both feedback and scheduling. And so just highlighting the entire relationships between them. Next part that we do, workflow, understanding, POV, so what we have is that first, whenever there is a new feature being added, allowing participants to sign up for event updates, so what we would have is information from the relational database is updated. With the participants registration, that is updated in the messaging queue. And then sign up triggers. An update in the schedule, both stored in the, if we go up, since we already know the document database focuses on the event details, and since caches are already connected with the document, schedule both stored in the cache and document database. And so yes, I'm just gonna put it over here, cache, queue, relational database, and the document database. So we worked our way from previous, since we had to divide up between exactly how each component would flow through in the relationship if we were to give a point of view perspective. And finally, the third will be handling faults and failures. From a hardware, software, and human side, looking at each of the steps from our workflow that we have from the beginning, middle, and end over here, highlight all faults. All faults which can lead to potential failures. There we go. So let me just move out here to showcase.
There we go. And so, yes, this was practice problem number 2, and this was our video on the concept of data locality and hybrid databases. Thank you very much for taking time to be able to watch this. If you found this helpful, be sure to, and feel free to, like and subscribe. If you have any other questions, feel free to put them in the comments section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we will be going over the system design course today, focusing on the concept of data convergence. Now, the convergence of document and relational databases marks an innovative period in data management where the two paradigms start to integrate features for a more efficient and versatile system. Relational databases, traditionally strict in schema and adept at relations, have started to adopt features like storing XML and JSON. So by the concept of data convergence, we are focusing on combining relational and document databases to put features together. For relational, for instance, databases combine components of document databases such as XML or JSON as an example. And it's leveraging on flexibility and performance. This allows relational systems to manage data that is not strictly structured, offering a more nuanced approach to data storage and retrieval. Document databases like Rethink database, which is a document database, have begun to include relational-like features such as join operations. I'll just use a different color. Rations. And structured schema with flexibility. Overall, they are a document database which include components of relational databases. The emerging trend reflects an underlying principle. Different applications require different data model characteristics. Different applications require different model characteristics. By combining the strengths of both relational and document models, a hybrid system can provide the best fit for an application's needs, optimizing performance and providing more complex data interactions. The advantage of such hybrid systems is that they offer developers the freedom to use the most efficient data management features from both worlds. So basically, hybrid data systems combine the best of both worlds. So yes, here we go. Let me just zoom out a little bit more. Oop, a little bit too far. There we go. A little bit more. There we go. So now let's go over a concept example to be able to solidify our understanding. So let's imagine we're running a multimedia content platform that stores users' profiles, video metadata, and user interactions. In the past, you might have used a relational database to manage users' data and separate document databases for the unstructured metadata of the videos. So the past, use relational databases for structured content and media, media/data, and document databases for unstructured media. Slash metadata of videos. The relational part would handle the relations, like which users liked which videos, while the document database would manage the complex nested metadata associated with each video, such as likes, subscriptions, or views in general. Relational would handle relations which user liked which video, and document show present data such as likes, dislikes, or number of shares. Just using that as an example. Now, with the convergence of database models and focusing on a hybrid system, you can use a single hybrid
with convergence instead of multiple databases can use a single hybrid database. Where within the system you store user profiles and their interactions in a relational manner, ensuring that the data integrity and relationships are maintained. Relational databases allow data integrity and relationships fully maintained. Simultaneously, the same system allows one to manage video metadata with the flexibility of document models. Document models provide flexibility. The setup simplifies the infrastructure and queries across different data types, making the development process much more streamlined and efficient. So let me just clean this part up. Now, to be able to solidify our concept understanding with data convergence, let's go over a practice example. So let's assess the nature of the data with focusing on an e-commerce platform. So let's imagine we are tasked with designing a database system for an e-commerce platform that needs to efficiently handle product data, customer information, and transaction records. The products have diverse attributes and require a documents database for flexibility. So the e-commerce platform requires a document database. And since we were dealing with a hybrid monetization, we also need a relational database component. So for the document database, it needs it for flexibility, makes sense. And have present data available, consistently updating. We just put down available. Well, meanwhile, the other component of the whole system that we need to consider is understanding about customer information and transaction records, which are best handled by a relational database. So relational database will be using the customer info and transaction record. And as we knew before, every data system needs a database, cache, and queue. So overall, what we need to do is that we need to design a workflow process to illustrate how one would leverage a hybrid database to handle an order process from the moment a customer places an order to the final transaction completion. So I'm just gonna put this right here. Whole customer walkthrough with hybrid, convergence for our data system. And so the steps and entities that we're going to be going through, we will be going through actually 10 steps throughout the entire process. So this will be a bit long, but it will give us a thorough understanding of what it means for hybrid convergence as well, understand more between what hybrid type of resources are there for document and relational databases to fully create our system. And so the first step that we're going to do in terms of actually designing and getting our system running is that we always need to identify key relationships. And as we know, for every data system that we have, we need a database, cache, and queue. A queue to handle actually, since we've already went through the previous video, the queue, the messaging queue, mostly relates to relational databases. And for a cache, namely, if we need flexibility in data that is already present, we would go with the document database. For present and updated information. And so we already identified the key relationships. Really, we need to understand the data needs for the organization and determine what types of data we would need to store, how it will be accessed. So just going over the questions, sometimes if there are products that are showcasing, like for instance, a preview reel, namely, we can go back at our previous example that we've already stated for the social media platform. For dealing with unstructured data, we can use a document database, but for more structured data, we would go with the relational database. So always remember, it's always dependent on the data. Relational databases go with structured data. And meanwhile, document databases always go with unstructured data. And so we would fit our data depending on the nature of the relational and document databases as well. Fit the data accordingly and know about the strengths and weaknesses for each and find the right fit. Find strengths and weaknesses for each database for efficiency. Now, the next part that we're going to use is actually figuring out the resources. We are going to choose a fitting database. Since we already know that every data system requires a database, cache, and queue. First part, and I'm just going to list out pretty good database resources that can abide by our needs for a relational and document database, ultimately to be able to go through. So what we could do, and I'm just going to be grouping them all together, a relational database I'm just going to list these examples right here. That can include, actually I'll use a different color over here for this part, and I'm just going to go with orange. Okay, relational databases include the following. My SQL, they always focus on structured data. Post, GRE, SQL. Then SQL Server. Then what we would do is that we can do with document databases. And a lot of them merge on NoSQL. So just stating in particular, so NoSQL. That can also include MongoDB. Cassandra. Or Couchbase. Then we can, another one is called, let me just pull this up, in-memory databases. Which would include Redis or memcached. And graph databases. Which include Neo4j or Amazon Neptune. And time series databases. Which include InfluxDB or Prometheus. And I'll put links for every single database in the description as well for further resources at the same time. But to be able to go through our example as well, the third part that we're going to need is that we're going to design our data architecture. We're going to determine how the data will be structured and stored across different database types. Determine storage across database types. And then we'll decide which data will be stored in each of the databases based on factors such as data model, scalability, performance, and query requirements. So we're going to figure out our trade-offs for each database for, just name, performance, scalability, data model, seeing if it's the right fit. I'm just going to put in fit right over here. And query requirements. All right. Then obviously the next step that we will be doing after our design is to focus on integrating databases. And when we integrate our databases, we're going to implement mechanisms to enable communication and data transfer efficiently between different database types. So we will implement mechanisms for data flow. And communication between database types. This would include some of the following examples. We would use ETL, which is extract, transform, and load. Which are a series of tools. ETL tools are tools which allow transfer data between different databases to be able to fit in with relational and document databases merging together. We could also implement APIs. For data transfer. And we could also utilize built-in features of certain databases, or utilize inbuilt features of present databases. We are using. And then what we need to do afterwards, we're going to do data synchronization. Where we establish a process for keeping data synchronized across different data types to ensure consistency, and implement replication. Across different databases for scalability. And updates for real time / scheduled intervals for data implementation and retrieval. Now, the next part that we would need to do, implement security slash, or actually and I don't know why I did that. Implement security and failures slash faults protocol. So we would set up monitoring tools to track performance and health of our data system from a hardware, software, and human side. And we would implement security features to protect data across all different data types. Or database types, I should say. Actually, data types, because we're dealing with caches and queues. So, since we'll be doing databases, caches, and queues. The next part that we have, step 7, is going to be monitor and maintain. Maintenance. Monitor and track our hybrid data system. And establish maintenance procedures for regular updates. Next, we need to test and optimize. Test the hybrid system for performance, scalability, and reliability requirements. And continually improve performance and efficiency. Step 9. Step 9. Document in training. Need to document the architecture, configuration, and maintenance of our whole hybrid data system. And we need just to provide training for all data architects for communication. On procedures for fault/failure protocols. And finally, step 10, we always focus on scalability and flexibility. Where what that means is that we need to consider future updates, for growth and scalability. And regularly review and update database and data system requirements. So let me just clean this up for you folks so you get all the steps in, since we did do a lot. And so I'm just going to go through this entire part. If one needs to take screenshots, by all means, feel free to. So just going through each of the steps, because I know we did a lot. I'm also going to put the steps in a text description down below. So feel free to be able to use that as reference as well. This is just part of the lecture series of what we have for our notes. If you want to take pictures or you want to be able to follow along accordingly while writing the notes to help cement the concept, by all means go for it. So pause the video, feel free to actually take screenshots of all the steps necessary for your own personal notes as well, just for reference as well, because I know we did a lot. So this is just giving an overview for the hybrid convergence for the e-commerce platform over what we need in terms of the process when combining both relational and document databases, and then also giving an overview of some of the resources at the same time. The links will be for all the resources in the description below, so you can check them out, namely, and get a further understanding between different databases that are used to be able to build out the database cache and queue for a whole data system for not just an e-commerce platform, but for general approaches as well. So again, feel free to pause the video to get this information down, because right over here. Yep. All right, now let's go over a second practice problem to be able to help solidify our understanding. Except for this time, we're going to be focusing on creating a database within a specific realm which requires a higher amounts of regulation. Namely, hospitals and healthcare have to abide by HIPAA regulation for the sake of data privacy in the United States. So we will be focusing on exactly creating a data system. Particularly in this practice problem, we are tasked with creating a hybrid data system, which is HIPAA compliant, and for every data system that we have, we're always going to need a database, cache, and queue. And then as a result from that, since we were dealing with a hybrid data system, emphasize that point, that means we're both going to have a relational and document database. So overall, let's imagine that we are creating a hybrid database system for a healthcare management application, and this system must efficiently handle sensitive patient records, facilitate appointment scheduling, and securely maintain medical histories. We need to create a data system which complies with HIPAA regulations to ensure protection of personal health information. So I'm just going to put this right here. Actually, a different color. Personal health information. PHI. Just going to abbreviate it for that. And we will create a plan that utilizes a hybrid database model, combining the strengths of both document-based and relational databases as well. So overall, we'll be going through a 10-step process as like before to get a further in-depth understanding of how to create a hybrid database system. And within the 10 steps, we're also going to be emphasizing our point of HIPAA regulation, where it can also abide by other domains as well, since we're focusing on domain-driven design. So let's go over these 10 steps. First step that we need to do is abide by compliance and data requirements. Typically that involves conducting a HIPAA compliance risk assessment, to identify potential PHI, personal health information, and implement measures to mitigate risk. And then that means we also need to identify types of data within personal health information that can also abide by appointment details, medical histories, and determine how they'll be stored, accessed, and protected. So overall, we need to determine how personal health information is stored, accessed, and protected. Step 2, we need to do database type selection. And as in the previous example that we did, we went over a different set of series of databases that are available for both document-based model and then relational-based model as well. So in this case, we're going to be focusing on choosing a document-based model first, data model or database, and choosing a relational database, there we go. We can choose MongoDB for the document based for flexible patient record. For both storage and retrieval, since there are other components of data that we also need to get from PHI. And a relational database that we can use is that we can use PostgreSQL. And since that can be stored and doesn't really have to be accessed, and there's only one point, and structured data, we can use appointment details. For remember, relational databases always focus on structured data. And document-based databases focus on unstructured. And then we also need to make sure that both databases abide by HIPAA regulations and they require audit controls. And they also need to have established business associate agreements. To handle personal health information. PHI, right over here. Then the third part that we need to do is develop architecture design. And with architecture design, we need to map out each type of data that will be stored, accessed, and retrieved. Assess basically all the data. All the data to be stored, accessed, and retrieved. And that means, in particular, if we're storing patient information, that means we'll have to work more with the document-based model for a little bit. But for relational databases, let me just put this over here for document. Oops. Document database. Then for the other part, for scheduling, we go with relational. And since we already have those parts already established, we would then implement indexing strategies. One second. There we go. Implement indexing strategies for both databases. That's also going to mean, since we're focusing on HIPAA regulation, that means we need to design the system to include mechanisms for automatically logging off and encryption key management. So we need to apply encryption key management. And anything with patient records always needs to be encrypted. So that's just pertaining for both, and that's just for the sake of the architecture as well. Even if we're implementing new features such as relating with the front end component to the back end of already storing our data in posteriori SQL and MongoDB as well to be able to combine for our hybrid database. And so we need to integrate for communication for the next step. So step number 4, integrate data flow and communication. So we can have secure, HIPAA abiding, I misspelled HIPAA for a second. I apologize on this. So we need to have secure HIPAA abiding API implementation if we choose. That means we're also going to have to apply audit controls. Access logs. And data integrity. We can also, and we kind of have to use this, we need to use middleware for data transformation. And ensure the exchange of personal health information is encrypted and traceable. So we use middleware for data transformation for the sake of encrypted personal health information. And then for communication channels, we need to abide by HIPAA's security rules transmission. I'm trying to use a different color. So HIPAA security rules transmission. Sorry about that. Just want to clean up and make sure we're on the right track. Apologies on that. Rules. All right. Then the next part that we need for step 5 is going to have to be data synchronization and security. So data synchronization and security. Where as a result, we need to implement real-time data synchronization. To audit trails for PHI updates. And we also need to develop robust security protocols, including, well, as stated before, encryption, access control, and frequent security audits. All right. Encryption, access control, and security audits. And obviously, so this is for implementation. For security. And so for the next part that we need to monitor and maintain for mitigating potential faults which could lead to failures. And then that means creating regular backup schedules and disaster recovery plans, abiding by HIPAA's regulations. So that means monitor for anomaly detection, for all three of hardware, software, and the human side too. And then we would then focus on testing, optimization, and scale ability, where this part performs comprehensive testing to verify HIPAA's compliance and security. There's typically a HIPAA layer that one needs to go through to review database performance and scalability. So we review database performance and scalability. For HIPAA compliance, and data transfer, abided by all layers, including HIPAA compliance. Layer, because there has to be a series of protocols that one needs to put in terms of the data flow going between the different databases that we're using, and sensitivity of the patient's health information, the different types of data that we're using for both our relational and document databases as well. The next part being for step 8, documentation, consistent documentation. It's just by principle, add comments. For updates as usual. Because, I mean, you have to abide, if you are dealing with patient's health, you have to consistently comment as a result from any changes, or patient health records are also implemented as well, since also insurance policies at the same time. The next part that we need, after we go through the entire relation, we need to do a fault tolerance and redundancy planning. Where in this, we design fault tolerance systems. Design for fault tolerance. Again, always abiding by the hardware, software, and human side as usual. And the technique that we use is going to be called RAID. So the RAID technique is redundancy array of independent disks. Redundancy array of independent disks. And we use RAID, redundancy array of independent disks, for data storage to protect against the data loss from drive failures. Used to protect against data loss and or drive failures. And then finally, for step 10, we have to develop comprehensive error logs. Handle the mechanism for any fail-safe protocol. Handle mechanism for any fail-safe protocol. And this is also abiding by HIPAA compliant error handling protocols. There we go. So let me just clean this up for you folks so that way you can all get a bigger picture of what we are facing. Just give me a moment. Okay, so I know this is a lot of information, but it's for us to be able to get a thorough understanding. Hang on. There we go. Okay, let's just zoom in. That way you folks can actually see the steps accordingly. And I'm going to move to the right. So again, feel free to pause the video, take screenshots if need be, as always. All right. Clean up more of this. There we go. All right, here we are. Again, I'm going to move slow, and if need be, feel free to take as many screenshots as need be. So I'm going to move from the left all the way to the right. So this is what we have. You create a hybrid data system right over here, and I go through the 10 steps. Abide by compliance with data requirements, database type selection, choose a document, choosing a document-based database where we focus on unstructured data, choosing a relational database with structured data, abiding by HIPAA regulation and patient health information. Third, we need to develop architecture design, assess all the data to be stored, accessed, and retrieved, and it's a document database. For scheduling, we will use a relational database, implementing indexing strategies for both databases, and we have to abide by a HIPAA regulation to apply encryption, key management. That's a security protocol. Step 4, we integrate data flow and communication, have secure HIPAA abiding API implementation if we choose. There might be specific ones. We apply audit controls, access controls, or access logs, and data integrity. And we use middleware for data transformation for the sake of encryption, for patient health information. Here. And for communication channels, we have to abide by HIPAA security rules for transmission. Step number 5, we do data synchronization and security, implement real-time data synchronization audit trials for patient health information updates. We have to employ encryption, access control, and security audits, which is just basic implementation for security. We monitor, maintain for mitigation of potential faults which could lead to failures. We monitor for anomaly detection in the hardware, software, and human side. Step 7, testing, optimization, and scalability. We review database performance and scalability for HIPAA compliance and data transfer, abiding by all layers, including HIPAA compliance layers. We have consistent documentation, which means we just need to add comments for updates as usual, since we are dealing with high regulation environment. Number 9, we have to implement fault tolerance and redundancy planning to design for fault tolerance in hardware, software, and human side. Typically in hospital management, there's RAID, which is redundancy array of independent disks, which is a backup protocol to be able to store patient information or any other means of information that we may need for the sake of hospital records. And for 10, we need to develop comprehensive error logs to handle handles mechanisms in a fail-safe protocol and abiding by HIPAA-compliant error handling protocols. So I'm going to zoom out, go from the left to the right again, except for more of an overhead view. And again, feel free to pause, review the entire notes right over here.
There we go. Again, feel free to pause to be able to get this. And so, yeah, that was practice problem number 2. And this was implementation for hybrid databases overall, and convergent document and relational databases. Thank you very much for taking time to be able to watch this. If you found this helpful, be sure and feel free to like and subscribe. And if you have any other questions, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we will be going over the system design course today, and today we're focusing on the concept of query languages. Now, in the realm of data management and retrieval, query languages play a crucial role. They are mediums through which users communicate with databases to fetch, insert, update, or delete data. So, query languages. They're designed to fetch, insert, update, or retrieve data, and also delete. So query languages are designed to fetch, insert, update, retrieve, or delete data. And among the various types of query languages, SQL, which stands for Structured Query Language. Let's do a different color over here. Structured Query Language. And as we know, SQL is also used widely for relational databases. And for every data system, we always need a database, cache, and queue. So, SQL stands out as a declarative language, contrasting sharply with imperative approaches seen in older systems, such as what we have talked about with the codicil system. So, for example, so we have already stated that SQL has already been proven to be superior compared to older systems, such as codicil beforehand. Let's move this over here. Give me a second. And I'll just minimize this. Mostly because of the ability to be able to search and modify data is a big reason why. And in previous lectures, we have already mentioned about the history between the establishment of relational and document databases, and how relational databases emerge superior compared to the traditional setup of codicil. And the distinction is fundamentally alters how queries are constructed and how databases interpret and execute these queries. So in general, in order to actually execute these query languages, imperative programming in languages such as Java, Python, or C require programmers to explicitly outline the steps needed to achieve a desired outcome whenever we are communicating with a particular database. It's much like in the case of providing instructions over saying, I want this piece of information from where I'm standing, and this is what I want it to do. And it could be of a variety of different functions. For instance, if you are a marine biologist looking to filter out sharks from a list of animals, one would typically iterate over a list and check each item's family's attribute and collect the matches. So just to give an example, 1 second. So we would iterate through a list
to get data, for example, I'll just use a different color for this. EX marine biologist searching for a list of sharks. There we go. And conversely, declarative query languages like SQL and combined with theoretical algebra, they base the operation on multiple principles and instructing specifically of detailing how the process is done over how would the language in of itself extract the data, and then focusing on what the desired end goal is. So with SQL, is made to retrieve a set amount of data from a database and to instruct the database on how to search. It's mostly just whenever we are talking about queries in general, we are trying to focus more on actually retrieving the data and communicating directly with the database. So overall, we are focusing on communicating with the database. The database. And also, languages such as SQL naturally are pretty handy when it comes to parallel execution, such as whenever one needs to either make multiple queries or also focus on actually achieving, for instance, a desired task that requires multiple computations, such as leveraging multiple CPU cores, or utilizing distributed systems whenever one needs to, for instance, create a certain application or create a model, depending on exactly what one wants to build. And while such code might be used to be able to alter different queries and also execute parallel distributions, there might be significant restructuring declarative queries that are initially having a first-hand assumption, but there needs to be further depth to be able to see exactly what explicitly is going to be retrieved within the database and what series of tasks need to be executed. For the rest of the lecture series, we're also going to go over further concept examples that will actually demonstrate some SQL code, which are actually, aside from the syntax, are pretty intuitive, but really we're just trying to search directly within the database to achieve and retrieve what we are trying to obtain. So let me just zoom out of here. Apologies on that. Oop. Those are for later. And here we go. Here's the first part. There we go. Now to go over a concept example, let's imagine a library database containing millions of records, each representing a book, author, genre, publication year, and availability status. A librarian wants to find all available science fiction books published after 2000 for a themed display. We use an imperative approach. The librarian would need to script a detailed procedure. One, they need to loop through every record. So, one, loop through every record. Check the genre. And publication year. Then check if the book is available. And if it's available, we collect it. And so we have a following example up here for the SQL script. By all means, feel free to take a screenshot and be able to put it in your own notes as well, where we are selecting from the whole library of books, and we're looking specifically in genre. And mind you, we are focusing on a relational database as well. So we have a relational database query. And with the relational database query, we already have a whole library of books that we're going through. And another component of the relational database is going to be a genre. And we're looking specifically for science fiction as a genre, because we have already documented that inside of our database. And also, we have a publication year as well to be able to specify when it was already published. And we're checking to see if it is available. If it's available, it's true, and we collect it, and we have these conditions that are already set up in place. So typically in JavaScript or Java, for instance, you would typically have a for statement to be able to loop through a given list, but SQL makes it very intuitive to be able to write out specifically if we want to select a specific book with a specific genre and publication year, and we're checking to see if it's available. If it's available, we collect it, which is the true statement, the end goal that we have. So we already have a genre, that's one condition, a publication year, and we're checking to see if it's available. So we have 3 different components that we're seeing to check if it is ultimately available. So let me just erase this to be able to showcase what we have: science fiction, publication year, and is available for true. And if it's true, we collect it. So to be able to submit our concept, let's go over a practice problem. And this time what we are doing is that we are creating a university database storing information for students. So just be able to go over. We are storing student information for students in a university. And while we are doing that, we are focusing on the information of students, courses, and enrollments. The database needs to generate a report of all the students who have enrolled in a specific course, such as Introduction to Databases for the upcoming semester, and this report should include the student's ID, name, and the course details. So actually, to be able to help highlight this, I'm going to move this ID all the way to enrollments. One second. There we go. All right, and so what we have the following SQL query over here that's really just focusing on the students or what we are facing. So we already know that we are selecting students based on the ID name right over here, the course name, and we also have a course semester at the same time, since we are just using that for small detail as well. And so what we are doing is that we are focusing on key components within a relational database, such as the students, enrollment, and courses, because these are fields that are already created within our relational database. And so what we're doing is that we're using the from command in order to actually be able to call upon a relational database the students, and we have to combine the enrollments and the courses as well based on the student's ID that we already have.
And this dot ID is really pertaining to the field of students that we have based on ID, name, and then also the courses based on course name and course semester. So this ID technically is also in the name. There you go. Now it looks like the course ID is already, based on enrollments right over here. So what we are doing is that we're selecting within our relational database to be able to, one, understand the join operation in SQL, which is essential for combining rows from 2 or more tables on a related column. So to be able to give a breakdown, join represents combining two or more rows from a table and in our example we need to join 3 tables: students, enrollments, and courses. So these are 3 tables altogether in our database. And the enrollments table acts as a bridge between students and courses. Equals a bridge between students and courses. And it's mostly just based on the records of the student's ID and the course ID. So let me see if we can move over a little bit more. All right, based on the student and course ID. There we go. So technically the SQL join clause is used to combine the rows of 2 or more tables in conclusion. And it's just based on joining the operations to connect the students table and enrollments table based on student ID column. So it allows us to associate each student with the respective enrollments, and we join enrollments with the courses also based on the course ID. And to be able to break down further on this, we also have the, let me see if I could just move over a little bit more. We have the where clause finally. And where represents the filtration of the data Let's see if I can just move this over a little bit more. There we go, a little bit more. Okay. Yep. The where clause in SQL is used to filter the records to fulfill a specific condition. Here it serves two purposes. So I'll just put it right here. Two purposes. One, it only specifies what we are interested in the course name. Specifies what we are interested in. Course name wise. And then the second part pertaining a double filtration for the semester. Hence we already have the name and the course semester as well to get what we need for where. And overall, the double filtration ensures that the report generated will exclusively contain records pertinent to the specific course and semester of interest, therefore allowing us to be able to get a targeted query to be able to get specifics on what we are searching for. So let me just zoom out. There we go. And let me erase this. And so now let's look at our second practice problem. Now let's consider a different situation where the university wants to identify students who have not enrolled in any courses for the upcoming semester. This is to reach out to them with information on course registration deadlines and academic advising resources. So we are focusing on students not enrolled. And so based on our query that we already have, we already select within our students databases, and we're using the from students in this table, and then we have left and join, which is what we will be focusing on. So with the concept of left and join, in this scenario, the concept of left join is becoming pivotal. Unlike inner join, where we just have regular join and what we already explained in the first problem, a left join ensures that all records from the left table, so it focuses on the left table, are included in the results set, even if there is no matching record on the right table for students enrollment in fall 2024. The left join clause in SQL is designated to return all records from the left table, so as specified before, and the match records from the right table are enrollments. The results become null. Sorry. From the right side if there is no match. And then, as well, going through our query, by specifying the semester in the on clause of the left join, we filtered the enrollments at the joining stage itself, focusing on fall 2024. The condition where enrollment course ID is null ensures that we only select those students who have not enrolled in the matching courses. So, focusing on students not enrolled. And we use null for that. And then the second part that we also need to consider as well is the where clause that we have. So the use of where enrollment's course ID is null is focusing on students that are just overall not enrolled. And this is just our basic practice problem that we have, just with different SQL queries. And SQL is pretty intuitive by nature whenever we are manipulating data and or trying to extract data. We're just giving databases instructions on what we are looking for specifically to be able to search throughout the rest of our database that we need. For every data system needs a database, cache, and queue. And so, yes, this was just a concept of query languages. Thank you again for taking time to watch this. If you found this video helpful, be sure to like and subscribe, and feel free to. And if you have any questions, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye. Hello, everyone. Today we will be going over the Systems Design course today, and the concept that we are going to be focusing on today is map reduce queries. So, when we're talking about map reduce in programming model design, we're focusing more on processing large data sets with a parallel distributed algorithm on a cluster. So you're focusing on processing large data sets with a parallel distributed algorithm on a cluster. And the following model for MapReduce querying is based on two main functions. One, the concept of the map, which is to process and transform data coming as an input. And the second part, literally in the name, is reduce, which what they mean by that is aggregate the result. So overall, just giving a technical understanding, in the context of NoSQL databases like MongoDB, namely, and or CouchDB, MapReduce offers a flexible way for a query aggregate data across many documents, filling a gap between declarative query languages and imperative APIs. The strength of MapReduce lies in the ability to distribute data processing tasks across many machines, making it highly scalable and efficient for big data applications. So if I were to give a vivid example, say for instance we're mapping the ocean, to be able to just give a vivid example. If we were to have a large map of data within present time in of itself, it would be beneficial for us to be able to take in the following input data and figure out how that we could actually break that data into various chunks as well. And this is where map reducing actually comes in. So the strength of MapReduce lies in the ability to distribute data processing tasks across many machines instead of just having one, making it highly scalable and efficient overall. So instead of one machine, we have multiple machines processing the input data. I stay right here. So we have a map following input data over here, and we have multiple machines to finally give out our result. As stated in this image over here, notice we have our map reducing, we shuffle out that data, then we have our given machines as well to also aggregate our final result. And so unlike traditional SQL queries, MapReduce operations involve writing snippets of code that the database executes. And this allows for complex data processing and aggregation that might be cumbersome or inefficient with just a standard SQL. So put this right here. MapReduce is efficient for no SQL applications. And again, as stated before, mapping with the ocean, we'll take the example even further of taking marine biologists tracking shark sightings across months, and would like to utilize MapReduce to aggregate observations by month, summing up the total number of sightings. So EX marine biologist summing up
all shark sightings per month. So overall, despite its following power, MapReduce operates at a fairly low level of abstraction, requiring developers to write specific functions for mapping and reducing data. So this really comes in with writing functions to map and reduce data. This can include complexity and potential for error, especially when coordinating these functions for complex queries. Moreover, the model enforces purity in these functions, and they cannot perform additional database queries or have side effects, ensuring reliability and predictability in distributed environments. So interestingly, as NoSQL databases evolve, they often reintroduce SQL-like query capabilities. So for instance, MongoDB added the aggregation pipeline. So I'm just going to put this as a side note. Added aggregation pipeline in order to have a more declarative way to query data that resembles SQL's expressiveness and way more and a stated comfort for relational databases as well. But it's interesting enough that they rely on JSON-based syntax, which is great for document databases as well. So relying on JSON data. And this following evolution suggests that while MapReduce is powerful for distributed data processing, there is still a continual need for more simpler and more intuitive query languages. Even in the NoSQL system, eventually there'll be something that will be able to not only just be able to handle complex modes of data and how it's going to be processed in real time, but also there's obviously going to be updates with further languages as well. And that's where you come in. And this is also why you're doing this course. So let me just zoom out to be able to help cement this concept right here. And feel free to take a screenshot of this, and we'll head over to our concept example with some JavaScript. So now to be able to solidify our understanding of map queries, let's go over a concept example. So now let's imagine we're a marine biologist using a database to track shark sightings. Every time we see or observe a shark, we need to record the following. So we need to record the date, species, and number of sharks seen. We wish to compile the data into a monthly report that indicates how many sharks have been sighted per month. So we are doing a monthly report for sharks sighted per month. And ultimately what we are doing, and there's already a JavaScript that is already a script that has already been made, and so we're just going to be breaking down over what has already been made to go further in depth. And so overall what we are doing is that the following code is made to be able to store the following values in a key value relationship. But to break down over what we have, so we are tracking the sharks per month, and we're actually just keeping track per year and month as well. And what we are doing is that inside of our function map, we are emanating a key value pair
where the key is the string consisting of the year and month of the observation. So year and month are strings. Right over here. And we're storing the instances whenever we observed. And the value is therefore the number of animals observed. So this is the key, and the value equals the number of sharks observed. And the reduce function that we see over here sums up the number of sharks observed for each key, producing a total count per month. And it is set up in an array with the sum of the following values, hence the key value that we already set up in place right here as the parameters. We have the values over here. And so if we wanted to, in particular, run through this, the result is stored in a new collection called monthly shark report. That is our output. This is our query that we have for the number for sharks. It goes through the following functions that we have and then returns the value that we already set in place whenever we call upon our MapReduce function. So let's just go out here. There we go. Let me just fix this. All right. All right. So feel free to take a screenshot of this. And we'll move over to our practice problem. Now, to be able to go for our practice problem, we are given the following scenario. We have a database where we are observing marine life across several years, including sharks, dolphins, and whales. We need to generate a report detailing the number of dolphin sightings per month. So it's just in the context of dolphin sightings. And so what we need to do for our following steps, and I also have the JavaScript function over here, and we'll be able to go further in depth, but to give over the steps is that one, we need to write the map function. Two, we need to adjust the reduce function. And three, we also need to modify the query parameter. And so within our following JavaScript code that we have, when we adapt the map function to filter the observations, we're focusing on filtering the observations for dolphins. This involves checking the family attribute right over here, and of each document and emitting the year month key along with the count of number of dolphins observed. So since we are going throughout the rest of the animals, all we need to do really for the most part is similar to what we already did in the first concept example, except for we're just dealing with dolphins in this case. So it's just modifying the parameter, and all we need to do within the key value pair is we just need to simply change just the family of the dolphins over here to assess between just the number of animals and assessing between our string values of year and month. And when we adjust the reduce function. Overall, since we are using the same type of example that we have did in the previous concept example, there are no changes necessary. So we just move over to the parameters. For the reduce function, gives us our output. We set it up for our desired output. And all we have to do for the query parameter is we just literally did it right here. So very easy, very simple to do. And any cases for queries and databases, they're relatively straightforward, and they can also be redundant and reused as well for both document and relational databases. So let's just zoom out over here, and you can take a screenshot of practice problem number 1. And now let's go over our second practice problem. So in our second practice problem, we're given the task, which we will break down the following operation that we already have over here, where we are doing the same thing, except the key differences is that we are going to be focusing on the extraction of whales in this case. So what we will be doing is that in our scenario, we're focusing on generating a detailed report of whale sightings grouped by species and quarter. So focusing on whale sightings. By species and per quarter. Where a quarter is going to be 3 months. And overall, what we will be doing is that we will be extracting our JavaScript code that will be used for MongoDB and break it down how we could set up our following operations. So let me just expand this even more. All right, so going back from what we have done previously, as usual, what we will be doing is that we're going to be focusing on one, the map function, second, the reduce function, query filter, and finally our output. Just keep all the code together. And so within our map function, what we're doing is that the function is executed once for each document, in this case, each whale sighting, that matches a specific query. It constructs a composite key from the year, since we are using a string in this case, and quarter as well, calculated each month. So that means that we are doing a month, then this is our quarter over here, hence the variable. Then this is our key, and MapReduce functions like this do a key value pair, where the key is pertaining to the time, and the value is a number of sightings. The number of sightings. And so the key is used to group the sightings. Well, the function then emits the key along with the value of 1 to signify a single sighting. So we have key, and this is how we initialize for each sighting that we have, and then we regroup them together. And then for our next reduce function, we sum up all the sightings for each key that we have. And so our reduce function calls a function once for each unique key element by the map. Calls for each unique key element per map. And for the map function, I'm going to say we initialize our string variables for a key value pair. as specified by the key of the time, the value of the number of sightings. Then we will be doing a query filter depending on what we are getting, and similar with our parameter, we put in whales as what we want to get. And then we have our output, a quarterly whale report as specified by our following output. It's collecting the total representative sightings of whales. So we are outputting total collection of sightings of whales for a report. Query filter, we just filter by parameter. Of what we want. There we go. And overall, this MapReduce operation provides a powerful tool for aggregating large sets of data across distributed systems, especially when dealing with complex grouping and summarizing tasks like this one. So let me just zoom out. And then again, feel free to take a screenshot of the following as well. Let me just fix this and I'll make this bigger for you folks. Let's fix this up. 4 over here, 3 over here. There we go. And so, yeah, this was a video on MapReduce queries. Thanks again for taking time to watch this. If you found this video helpful, be sure and feel free to like and subscribe. If you have any other questions or queries, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone. Today we are going over a system design course today, and today we're focusing on the concept of declarative web-based querying. Now, to dive into our concept, in the world of web development, the distinction between declarative and imperative programming paradigms play a pivotal role. So declarative and imperative. Where declarative programming focuses on the what, and imperative programming focuses on the how. For largely in web-based querying, a large portion of it is curated towards declarative programming and is especially useful in tasks such as styling web pages and querying databases. Declarative programming allows developers to express their intentions on what should be done without specifying how to do it. This high-level approach is perfectly exemplified in CSS for styling and SQL for database inquiries. So CSS for styling, and that's just an example right over here, and SQL for queries. Overall, it offers a stark contrast to the more detailed and step-by-step nature of imperative programming found in JavaScript DOM manipulation and procedural database access methods. The essence of declarative programming lies in its ability to abstract away the complexities of how tasks are executed. This not only simplifies the developer's job, but also leads to more readable and maintainable code that's scalable, efficient, and reliable. If we were to go further in depth in CSS styling, developers define the desired styles for elements based on their state or properties, and the browser takes care of applying these styles. Similarly, when querying databases with SQL, the developer specifies the data they want to retrieve or manipulate, and the database engine figures out the most efficient way to fulfill the request. So, SQL, manipulate the data.
CSS styling, focus on front end styling. And now let's go over a concept example. And now to be able to submit our concept, let's go over a concept example. So in web development, there is a distinction between declarative and imperative programming styles. To illustrate the difference, let's consider a task of highlighting the active page in a website's navigation menu. So we are highlighting a website's navigation menu. And the following HTML structure that we have over here is basically just a series of lists that we would have depending on each item that we are able to make for a navigation bar, such as we have a home, about, services, or contact. And with the CSS, we can declaratively define the styles for the active page by specifying a class called active. Now, some people would say when they first look at the HTML and CSS code that the class active is not present, but this is where our JavaScript is actually going to come in. So to be able to explain in depth of the CSS script, the CSS rule will apply to a blue background and a white text to anchor any tag that has a and also specifically on that anchor tag that is a direct child of a list item to anchor tag A and the list item li. With the class active. This is a declarative approach because when you define what specifically you want the style to be without specifying how to apply it, instead you're just given explicit instructions. On the other hand, using JavaScript, the developer would make it an imperative approach over here. So the CSS over here would be declarative and the JavaScript would be imperative. So on the other hand, using JavaScript, what we are going through is that this JavaScript snippet illustrates over each navigation item and adds the active class right over here, indicated right over here, right in this point. So it's applying to all the components between each of the nav items that we have whenever we are calling upon active for each class list that we have. And where the anchor tag is, we're going to locate the active class and put it inside of this nav item that we have. So that way it's already making a declaration to the active status that we have within our nav item that we have specified in our CSS and communicates accordingly between the CSS and HTML files set in place. The following styles are applied directly through JavaScript and specifies exactly how the CSS would actually be applied for inside of our HTML file. The declarative CSS method is generally simpler and easier to maintain in general. Whereas the imperative JavaScript approach can be more verbose and error-prone. Easy to errors. However, the CSS approach allows a browser to handle state changes like the current page without additional code to manage these changes, whereas the JavaScript approach requires explicit instructions to manage the state. So just highlighting the differences between declarative and imperative when applied to web-based. So we already know, for instance, between CSS, JavaScript, and how they can be applied for declarative and imperative programming within our HTML file. So now let's go over a practice problem to help solidify our concept of understanding. So in our scenario, we're tasked with dynamically styling a list of items fetched from an API where items that are marked as urgent need to be highlighted in red. So we are doing a dynamic styling of a list. Every .urgent item must be listed as red. And so let's go over the basic definitions for how we apply this for declarative and imperative programming. So for declarative, focus on what, imperative, how. So what we need to do is going to be for the following. So let me I'll just go over here. Okay, so for step one, what we will be doing is that we're going to define the CSS script for urgent items. So let's take a look at our CSS script. So what we have is that we have a list item that we have in this case, and then we're also calling upon urgent, and for every urgent item we're also going to list as red. So we specify the color, so we go with declarative programming in CSS to specify what for the color. And then for step two, what we'll be doing is that we'll apply the class based on item properties. And so what we will be doing is that we have a class called list item. So technically in CSS, so this is just the HTML code that we got from the last example, but instead of the nav item, we are going to have our list item specified as the class that is right here. And then what we will be doing is that we're going to take this urgent listing, and that we are going to be modifying with our, let me just put this right here, HTML, CSS, and then JavaScript. And inside of our JavaScript, what we are doing is that we're doing an API call. So we're doing the API call for a list of items. And iterate through apply. Through and apply for the urgent call. And so what we were doing is that for every item that we have specified as a list item, right here, which would be inside of our HTML, we are going to put in an urgent, and every urgent call that we have for each list item that we have, whenever we are calling, it's all going to be turning red for our background color, while keeping the color white. And so overall, it's just a simple two-step process for what we would be doing to be able to see how we would apply in the concept of styling for declarative and imperative programming, where our first step focuses on declarative and the other part focuses on imperative programming in JavaScript. Let me just specify this over here. So this is imperative and CSS is declarative over here. And feel free to take a screenshot of our following practice problem, and we'll move over to the second one. And now, to be able to solidify our understanding, let's go over our second practice problem. So in our second practice problem, we need to highlight items that are newly added to an HTML list using a green background. So what we are doing is that we are highlighting newly added items with a green background. In our HTML web page file. And so, while going through this, we need to ask ourselves what's going to be declarative, and then imperative. And to go through the steps, step 1, we need to define a new CSS class for the new items. We do so within our following CSS script. So we notice that we have a list item that we have, similar to the class ID that we have in the HTML. And then we have a new item that we will have with a green background specified here. And then the text in itself, well, being white, but the background color is still green. This class follows the declarative paradigm, specifying the desired outcome for new items without detailing the implementation. So we focus on new items are green. Actually, I would say new items background. That is what? Or I should say newly added items. And then for step 2, we're going to dynamically apply the new class via JavaScript. And inside of our JavaScript file, what we are doing is that we're going to modify the item's processing logic to check for, is there a new item right over here. So we're adding an isNew property and apply it to the new class accordingly. So inside of our JavaScript script, we are scanning through the whole list of items that we have. And for every item that we have, is it going to have a green background? And what we will do through the JavaScript code is to apply the class in an imperative manner to be able to append a following list item. Within our item list, to be able to check to see if each of the following items that we are adding is going to have a green background. So we specify with new, and then we also have new up here. So all we have to do, and this allows us to be able to scale efficiently instead of going directly inside of our HTML file, we can just continue to add new items with a green background as well, whenever we want to list items dynamically via JavaScript. And that way it keeps all of our code efficient and easy to scale and manageable. And let me just zoom here. And so, yes, this was declarative web-based querying for our system design course.
Thank you again for taking time to watch this. If you found this helpful, be sure and feel free to like and subscribe. And if you have any other questions, please feel free to put them in the comments section. As always, take care. Cheers. Bye-bye. Hello everyone, today we'll be going over a system design course today, and today we're working with graph-like data models. Now, to be able to go over the concept of graph-like data models, it really focuses on the shift from tree-structured document models to graph-like data models, which are driven by the need to represent complex many-to-many relationships naturally. In graph-based models, the world is interpreted through two fundamental elements: vertices and edges, where the vertices represents entities and the edges represent relationships. So when combining both of them together, we already see that the vertices are the objects of interest, while the edges are akin to the relationships that bridge the vertices together, creating a web of interconnectedness. The interconnectivity is not just a theoretical concept, it's prevalent in numerous real-world scenarios. So let's consider social networks, for instance, where we have individuals, which are the vertices, form friendships or acquaintances, edges, with each other. There's the boundless realm of the internet, for instance, with web pages as vertices connected by hyperlinks. So I want to point it out for the internet as an example. We have web pages and hyperlinks, which are considered the vertices, and the hyperlinks as edges. And this is not also applied for the internet, but this is also applied for transportation networks, such as junctions, airports, or stations, and the vertices representing roads, which could also represent the routes for them to be able to get from point A to B. Overall, graph models excel where entities have diverse and dynamic relationships. So they excel with diverse and dynamic relationships. Let's move this out of the way. Let me just respell this. And overall, they provide a universal framework capable of encompassing various types of vertices and edges within a single unified database. Capable of putting relationships in a single unified database. Which overall streamlines the complex data integrations. This adaptability is why platforms such as Facebook leverage graph databases to integrate different types of user activities and relationships seamlessly. And we have an example.
One of the most complicated computations that we do on the site is the computation to tell how you're connected to people, right? Because, I mean, if you can imagine that's stored as sort of a series of I guess, undirected, it's not weighted, so undirected, unweighted pairs of ID numbers of people in the database. Then if you want to figure out who's friends with someone, you have to look at all their friends, right? So that's maybe like 100 or 200 people. But then if you want to figure out like who's a friend of a friend or what the closest connection is there, then you kind of have to look at the 100 or 200 friends of each of those friends. So it becomes, like at each level, there's another factor of n multiplied in, where n is the number of friends that each of your friends has. So you can see that this kind of becomes exponentially difficult to solve for the shortest path between people. So I mean, if you're just looking for a friend of a friend, that's n squared. If you're looking for a friend of a friend of a friend, that's n cubed. And I mean, that's something that traditionally was pretty difficult for a lot of the predecessor sites to Facebook. So And for example, Friendster had large problems with this because they were trying to compute paths 6 degrees out or like 7 degrees out. And I mean, that's something that when you're doing like N7th, like that just is really, I guess, very hard, and took down their site for a while. So I mean, one of the things that we kind of had in mind when we were figuring out how to do this was how do you distribute the database in such a way that this computation becomes manageable. So what we decided was that everyone on the site does most of their activity at the school that they're kind of based at. So if you're at Harvard, then like most of the people who you're going to be seeing or transacting with on the site are going to be at Harvard. It's actually probably like 90% of the stuff that you do on the site. So we decided to split up the databases and create one instance of a MySQL database for each school on the network. And
so overall, that is just a vivid example to be able to showcase graph-like data models overall. And every data system that we have is going back from most of our lectures. Every data system is going to have a database, cache, and queue to be able to have a data-intensive system altogether. Overall, employing graph databases has quite a set of unique perks, actually. So graph-like databases, let me just move out of here for a second. So the perks, for the most part, really come in handy. So other examples could also be PageRank. When you ever search on Google or Bing or whatever platform you use. So search engines. And then they can also navigate web pages based on popularity. There's also travel routes on a map. Whenever you're trying to get from point A to B destination, depending on what you're trying to filter. So there's filtering. Just to give a few examples over there. Just going to highlight that. But beyond these following examples, graph models offer something more. They offer a more natural and flexible approach to data evolution. As applications continue to grow and requirements shift, the graph model can be extended without uprooting its core structure, making it resilient overall for a long-term data management solution. So it's great for a long-term data solution. Just zoom out of here. There we go. Let's head over to our concept example to further cement this. Now, in our concept example, let's imagine mapping out a family tree or visualizing a circle of friends online. So overall, each person is a vertex. We have, for every single graph model, we got to know what are the vertices and what are the edges. In a family tree, the entities are going to be the family members. And overall, the relationships are considered the edges. Like, just how are they related? So overall, if we were to have a family member, we would, for instance, have mom, dad, brother, sister, all connected in a graph one way or another, such as mom, dad, they're connected union. You have brother, sister in one case, and that's considered a family. Just an example overall. So you can have a directed or undirected graph, weighted, depending on the context of what you are going for. But overall, if we were to, for instance, picture two individuals, let's take a further in-depth example. Two individuals. In fact, I'll just put this made over here. Sorry. Okay, excuse me. So now we're picturing two individuals. Let's call this person Lucy from Idaho.
And then Alan from New France. Despite their diverse origins, one being American, one being French, they share a life story together in London, a bond depicted as an edge in our graph. So we have Lucy over here, then we have Alan, all connected by a relationship that they have, that they were in London together at one point. So if we were to apply this in a graph database, so every data system is always going to require a database, cache, and queue. That's always a data system whenever you're deploying something. So if we were to put in a graph database, examples which come into mind that one could employ, deploying in the database, a graph model would be Neo4j, which would encapsulate the relationship, residence, and origin, so as parameters. Overall, respecting the varying granular, overall just respecting the different modes of diversity within the data that we have. We will also consider state and city as well, if need be, just adding parameters within it. Overall, this flexibility of the graph model allows us to be able to differentiate the structure, and we could have different regions in particular. So like the United States has a state and city, and France would have boroughs in particular, depending on where. And the graph model has the flexibility to be able to actually adjust between different parameters and such. So we adjust between different parameters. One second. It allows us to have a versatility based on the graph model. In a traditional database, such rich and intricate relationships might become convoluted, buried under a pile of join tables and foreign keys. It would just take a very long time to be able to actually find the relationships and be able to add on new parameters. So if we were to picture a database, namely, we can imagine it as like a MySQL database, as Mark Zuckerberg was also mentioning about it. It was very hard to be able to do and utilize, but the graph-like data model, or any database that relies on graph modeling, allows us to be able to make intricate connections and be able to add on more parameters that we could actually find and can join those relationships together. Excuse me for a second. So overall, as the application continues to grow, it allows us to add more flexibility depending on the intricacies of the following data that we need to be able to integrate new vertices and edges as the data universally expands. So if we're adding on more type of vertices and relationships, like for instance, Lucy's family wants to meet Alan's family. So we already have, we can have a series of one family over here, Alan and their family, and they're connected one way or another, in either an undirected or directed graph, depending on the context of the data. So let me just move out of here. There we go. And feel free to take a screenshot.
Now, for us to be able to solidify our concept, let's go over a practice problem for graph data-like models. So, in the context of social media and a social media platform, the graph data model is key to mapping the intricate web of user interactions, connections, and content flow. So, for graph data model, we focus on user interactions, connections, and content flow. Utilizing a graph database, so mind you, whenever we always have a data system, we always need a database, a cache and queue. So an example of a database that we could use would be something like Neo4j, which allows for a modeling of users, their posts, likes, and comments. So users, posts, likes, and comments. And follows as vertices with relationships between them as edges. So they will all have relationships. And whenever we have relationships, we always need to remind ourselves that graph data models always have vertices and edges. And we know that the edges pertain to the relationships of all the post, likes, and comments, for instance, and the vertices can also mean specifically the post's likes and comments, and also users as well. So we already have that in this context over here. So this setup enables a nuanced understanding of user engagement, content variety, and community formation. A distributed cache would leverage graph queries by messages and further posts and further comments as well to be able to update the current user interface and can provide instantaneous access to feed updates and notifications. So we would have a distributed cache for updated access. And the queue represents the user's actions. When interacting with the platform. So when interacting with the platform. So for step 2, So then the next step that we would need to understand is create a workflow diagram. And the workflow diagram would be as follows. When a user posts new content, the system employs a graph traversal. So when user is posting new content, the content is considered the vertices, and the relationship of that content is considered the edges. So we would also know about the network and fan out method. Remember our Twitter example and our fan out methodology. Which would be the edges. So overall, we will understand between analyzing the edges for connecting the strength and recent interaction of history. The platform will utilize content delivery by managing the most engaged followers and optimizing maximum engagement. There are updates to the graph database reflecting the interactions, and overall enriching with data on content popularity and engagement patterns. So, and then the next part that we would need to consider after we set up our whole database system that we've already set up in place is that we need to always consider faults and failures between the hardware, software, and human side. Consider all faults and all potential faults which could lead to failures. So we need to ensure that the platform's reliability involves safeguarding the integrity of graph data, crucial for maintaining user trust and engagement, and strategies to deploy redundant graph database nodes. So we need to deploy redundant graph-based, well, technically graph-based vertices and also handle traffic volume for reliability and scalability. And quick recovery from errors. From the hardware, software, and human side all together. These following measures ensure that the social media platform is resilient even under stress of viral content and rapidly evolving user networks. So let me just zoom out of here to give you a deeper understanding. There we go. And let's move over to our second practice problem. Feel free to take a screenshot as well. And now let's go over our second practice problem. So in our second practice problem, we're focusing on a map for restaurants using a graph data model. So the number of steps that we have to do, and I'm just going to go straight in the steps for this. So the first step that we got to do is understand. Let me clean that up and use a different color. The first step that we got to do is understand the connected components within the graph data model. So understand the connected components with a graph data model. And as we know, from every data intensive system, every single one's going to have a database, cache, and queue. That's right. Every single data system is going to have that. It's essential. It is needed. If you don't have it, you don't have a data system. Isn't it obvious? Anyway, for a map-centric restaurant discovery service, a graph data model illuminates the relationships between users, restaurants, reviews, and location data. And for every graph model, we always know that there are two types of parts that make up a graph model. We know that there have to be vertices and edges. Edges always signal relationships, and vertices represent entities. Edges, relationships. So for restaurants, in a map, we have users, restaurants, obviously. I'm going to use a different color for this. We have restaurants, users, reviews. We can go off on this forever. Use and locations, because we also have miles as more meters, kilometers, depending on which distance, really. And the relationships are always the edges. So the edges, for the most part, could be the relationship of the, it could be overall of the distance, the type of menu, all having different forms of connectivity as well. So locations, we put it as vertices, but then we already put in for the distances between them. The type of menus relative to the restaurants as well. Maybe they're grouped all together, or maybe there is just something that's connecting them. Maybe it's a franchise as well. So maybe you're looking at different franchises. Again, we can go off on between vertices and edges for the graph data model. So in terms of a robust database,
A good example would be of a Rango DB, Rango database. Where it facilitates advanced features like personalized recommendations, in efficient route planning for restaurant visits, and dynamic update for restaurant popularity based on user interactions. The distributed cache we would need for consistent updates and real-time access to restaurant ratings. So we can put in ratings, for instance. And the messaging queue would be bookings, for instance, timely updates for information and reviews. So this can also be messaging queue for reviews. And overall, this would be just the first component we need for a graph data model. So now the second step that we need to do is drafting a workflow for our graph data model. And the way we do that is that we need to consider the user searches for restaurants and how the user is going to be interacting. So we got to ask ourselves, how will the user interact? Between our whole data system. Between and within our whole data system. And we do so by understanding the social connections between location, preferences, and reviews. So we can do location, preferences for taste, and reviews. That's a filtration criteria that we actually understand between the whole graph network. And there will be consistent updates to capture new reviews and visits. And there's dynamic adjustment with restaurant rankings and visibility on the map. So there's also dynamic flexibility and adjustments. For restaurant. Ratings and reviews. With visibility on the map. Map data models are great for filtration. Graph. Yeah, graph data models are great for filtration. And finally, that we have to do for every data system that we already built out, we always need to consider the faults that may lead to potential failures. Consider all faults and potential failures. And we do so to maintain the service's efficiency and accuracy. We always need to look at the hardware, software, and human side. Prone to errors. And we overall need to figure out and understand more, aside from efficiency and accuracy. We need to manage the graph's data models, integrity, and reliability. So we always need to consider the integrity, reliability, and scalability.
Okay. And this overall involves implementing redundant storage. To be able to not only keep track of the user's logs and interactions within the data system for changes, but also if there are more restaurants being added, and also protecting current data if it's lost. The following precautions would also ensure that the restaurant discovery service maintains a trusted and open, up-to-date resource for users to navigate within their current preferences. So let me just zoom out and clean this up for you folks so you all get a deeper understanding between it. Let me just move 3 over here. There we go. Okay, and move this right here. And so, yes, this was graph-like data models within our system design course. And thanks again for taking time to watch this. If you found this helpful, be sure and feel free to like and subscribe. And if you have any other questions as well, feel free to put it in the comment section. And by all means, if you want to be able to refresh any concepts that you need to, or feel free to pause and take screenshots along the way, by all means do so. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to be going over a system design course today, and today we're focusing on cipher queries and graph queries. Now, to be able to give a breakdown overall over how we approach cipher query language and graph queries, and mainly we are focusing in SQL. Is that graph databases bring to life the overall intricate map of relationships that are inherently complex and interconnected. So we already know that graphs, databases can focus on relationships. And we also know that they have vertices, and edges. Vertices being the entities, and edges being the relationships. And so the language used to query graph databases is overall crucial to understanding how we extract the data itself. And it is where Cypher enters the stage, which Cypher is a declarative language focusing on the what for data extraction. And it's widely tailored for Neo4j's property graphs. So it's a language that allows us to define patterns in our data graphically and retrieve information with precision and elegance. Cypher's simplicity in syntax and its power in execution enable us to ask intricate questions about our graph data. Take, for instance, the search for individuals who have migrated from one country to another. Cypher handles this type of data and data extraction with ease, allowing us to traverse the graph with patterns that match our query conditions, much like a flashlight to follow a trail to the dark. But what if our data lies within the familiar yet rigid structure of a relational database? What about structured data in a database? Relational Overall, can we still emulate the agility of graph queries in SQL? The answer is a conditional yes. We can still traverse data in the database like a graph. But not as efficient. Because queries tend to take a longer time to be able to write out, and they tend to be more complex, as well as understanding how we apply recursion relationships between data extraction. However, this doesn't take away SQL's power and universality, but it does highlight the elegance of Cypher in the context of graph databases. The choice between SQL and Cypher is not merely on syntax, but also aligning with the most natural expression of data and also application and preference at the same time. So it will all differ. So let's just move out and feel free to take a screenshot, and let's head over to our concept example. And now to go over a concept example, let's consider tracing migration patterns. So let's consider a scenario where we wish to uncover migration patterns within our social network. Using Cypher, we can effortlessly de-alienate and extract paths of individuals who move from the US and Europe. Here in Cypher, namely, we're able to make it very easy and very seamless to be able to extract the name type along with the contents of it and be able to go through in a list type order. However, in SQL, we have to apply a lot of recursion, and this is pretty syntax heavy to be able to go into until we finally get to what we need to specifically get to. We're able to define clear relationships in Cypher. While SQL, on the other hand, applies recursion. Since given the fact that both Cypher and SQL lead us to the same destination, there is a bit of a different series of syntaxes that have to be applied whenever we have to take different paths. Overall, Cypher glides through the graph data model with extreme amounts of ease compared to SQL, since SQL largely has to focus on a declarative, needs to approach this with a declarative query. Cypher is able to mitigate that by providing more efficient syntax. And now to go over our first practice problem, let's focus on analyzing social media influence. So let's apply the concept of from what we have learned about ciphering and to this practical scenario. So we need to imagine that we need to analyze the influence spread in social media networks. And our task is to identify users who have migrated their content creation from one platform to another. So focusing on content migration. From one platform to another. And the entities we need to consider as well is that we first need to identify the pattern. Along with execution of the query. And what we have done really in this Cypher script is that we're matching users based on the content that they have created on platform A, and then also collect the followers within platforms, followers from said platform as well, Then we also need to match the content within platform B, and then overall collect the followers accordingly. And then we execute a query where we always start with match, as indicated over here. As indicated here, where we also we're able to identify and extract what specifically content and the followers as well from both platforms, and we return the collection of followers as well. So this is our first example or practice problem that we would show, focusing on the application of deciphering. And now let's go over a second practice problem. So in our second practice problem, we are tracking an ecosystem of business networks and exchanges. So we need to imagine a networked ecosystem where businesses interlink through partnerships, mergers, and collaborations. So we're focusing on business partnerships, mergers, and collaborations. And our goal is to track the evolution of these connections over time. So step one, and we have also already developed the cipher syntax as well. Step one, we need to map the initial state. Step two, you also need to follow the evolution. Of the business networks as well. And three, we need to understand the dynamics. When we have done so, we're able to label out specifically how the cipher would actually go. And remember, every time that we're using cipher to make a query request, we're always using match and then also returning specifically what we are doing. As we can see, it's a very strong declarative approach between matching between the business relationship and other businesses. So we get the business relationship right here. And then we can also see the other indicators such as timestamps as well, such as where we can have a start date, end date, and return as well. We match and then return as likewise. And so yes, this was the application of ciphering queries and graph queries in overall SQL in its present applications. Thank you again for taking time to watch this. If you found this video helpful, be sure and feel free to like and subscribe. And if you have any other questions as well, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone. Today we'll be going over the system design course, and today we're working with the concept of cipher query language. Now, cipher is the SQL for graphs. That is the first thing we need to label. So cipher is considered the SQL for graphs. It's a declarative query language developed for navigating and manipulating property graphs, especially within Neo4j graph databases in particular. Unlike SQL's rigid table-focused syntax, cipher is designed to express complex graph patterns naturally and unlike SQL's rigid table-focused syntax, it embodies a more intuitive way of handling data, reflecting how we can conceptualize and verbalize data relationships in the real world, and also be able to be adaptable for different parameters and flexibility within various forms of data. In Cipher, vertices and edges in the graph are described using a pattern matching syntax. So there's a pattern matching syntax, which also models after ASC2 art. Vertices are depicted in parentheses, akin to nodes or in trees. So in parentheses as
vertices, and the edges are arrows. With a description which conveys a relationship between each component of vertices within the whole graph. This approach is not only able to make queries easier to read and write, but also aligns with cognitive process of understanding connections and associations. Cypher's real power lies in the ability to articulate intricate graph traversals and relationships with ease, and queries that may be cumbersome in traditional SQL, such as if you have an expansive library on specific books. It's way more streamlined within graph databases, and especially when utilizing Cypher, namely, to be able to go off on different relationships depending on exactly what you are looking for, namely. So you may have different databases that may contribute from one area to another, or established relational databases as well that you need to go through to be able to get the specific information you're trying to recall. And the flexibility of Cypher allows us to extend query execution. So Cypher allows us to execute queries in a fluid and dynamic manner, in fluid and dynamic manners. And overall, this following abstraction allows users to focus solely on what their data retrieval or manipulation task is, rather than how. On the what over the how. And we know that this is declarative. Coming from our web-based declarative queries lecture as well, over the how. By all means, if you need a refresher, feel free to go back on that video. And this is just a following brief overview concept. We'll dive further in depth in exactly the intricacies between Cypher queries as well. So by all means, feel free to take a screenshot. Let me just clean this part up. And now let's head over to our concept example with some ciphering query language. Now, to be able to solidify our understanding, let's go over a concept example migration path. So there we go. Let's visualize a query using Cypher that identifies people who have migrated from the United States to Europe. So in this case, we have US to Europe. In our graph, each person is a vertex. So every graph data model, we are always going to need a vertices and edges. Vertices in this case, in context, where they are the entities, edges are the relationships. The vertices in this case are going to be the individuals. And the edges are the ones that identify the individuals. So we can just put in individual's identity. And as we have already stated, each person in the vertices is each vertice is a person, or vertex is a person, with edges representing their birthplace and current residence. So overall, birthplace and residence. And our goal is to follow the edges to identify individuals who were born in the US and now live in Europe. In SQL, such a query might involve multiple tables and joins. In contrast, Cipher, on the other hand, as highlighted by these examples that we have over here, since we are looking at birthplace and residence based on a person's identity, and each of the vertices represents individuals. Over here, so name, so birthplace, type continent, United States, country, Idaho state, and we have Lucy, and the relationship between person, born in, within, location. And we're able to see, in particular, between the vertex that we have and each of the edges represent a relationship and a following command that we have: born in, lives in, and this is all within the Cipher query language. So this match statement overall focuses on matching the pattern where a person vertex has an outgoing born in edge to a vertex labeled the United States, and a separate lives in edge to the vertex Europe. So we have lives in Europe, born in United States. This match statement not only scrutinizes and captures the essence of our search, but does so in a way that we're able to visually and see ultimately between the person and other parameters that we've also added within the Cipher query language, and then be able to make those matches accordingly to result in a query that is not only efficient but also intuitive, to reveal the names of individuals that have journeyed basically from the United States all the way to Europe. So feel free to put a screenshot for the following Cipher example that we have, since we already have a entity that we have already created with a series of parameters, and then we also have edges really focusing in on specific what declarative statements that we have to be able to see. So I'm going to put these as edges, and this one is a vertex. This whole thing would be considered a vertex since we're creating a whole entity inside of our graph data. This will be inserted in graph data model with loads of parameters, and this can also be used in the J. Let's clean this up. Again, feel free to take a screenshot, and we'll head over to our 2 practice problems to help cement the concept.
And now let's go over our first practice problem. So in our first practice problem, we are going to be ciphering for in the context of a business analysis. In the context, really, of a business application, suppose we want to identify patterns of customer migration across regions to better understand market trends. So what we are doing is that we are developing a business application with identifying customer migration. For market trends. And every graph data model is always going to have vertices and edges, where the vertices are going to be the entities and the edges are always going to be relationships. So in the context of the entities, it looks like the vertices are going to be customers, And in the context, since we're focusing on migration, it looks like other data that we will be looking for is going to be the region and or location. And the edges, on the other hand, will be focusing on really where each customer is going to be moving and each move they make. So customers movements. And so what we are doing is that after we have established our context, we need to fully understand, really, and our first step is understand how ciphering will be applied. So we understand how ciphering will be applied. And that really comes in the context of understanding the graph model, being applications and components of the graph model, which include vertices and edges, and how we are traversing through the data. So we already determined exactly what our vertices and edges are in the context of our business application, but when we are traversing through the data, so this is not going to be a something like a relational database where we are making a simple static query, really just finding particular components in a relational databases. Since we're making a declarative approach, we are traversing a living map of customer movements. So we are doing a living map of customer movements. And yes, this all needs to be updated in real time. Let's put this as an example right over here so we know the context. There we go. And now, as usual, we always know that every data system always has a database, cache, and queue. So a database, we can use Neo4j as an example. Cache, distributed cache, and messaging queue, tracking the movements. And so once we have done so, we're going to have to move over to our second step, which is formulating the cipher query. Now that we already know the context between our vertices and edges, the cipher query will overall, we're going to be matching customers who were born in as an edge right over here. I'm going to put in red, born in, and yes, it has to be all caps, born in, and I'm just putting the edge, which will be connected to a vertex. Representing the initial region. And also with the edge of lives in. Edge connected to a new region's vertex. So we have customer already moving between the initial region, now the region's vertex. So we already have a customer in particular that has a region already moving on the map. So we can have like a dot over here, and then the customer is already moving on the map, and we are already tracking between where specifically they are located on that map. And this overall is to aim to trace the customer's journey from one vertex to another. Now, finally, for the third part, analysis action. Faults and failures. So once we already put in our ciphering within our graph data model, we just make data based decisions based on info from the graph data model and always consider faults and failures. Yeah. Consider all potential faults and failures from a hardware, software, and human side. So let me just zoom out of here. There we go. Let me just move this over here. And clean this up for you folks. And again, feel free to take a screenshot of this so that we can move over to our second practice problem. Let me just clean some of this up. And so yes, let's move over to our second practice problem. And now let's look at our second practice problem, focusing on a social media network. So let's consider a social network where you want to study user migration from one interest group to another interest group or one page to another page. Let's consider the shift of trends of interest. So social media and media, users, and shift in trends. Every graph-like model, so it's going to have vertices and edges. The vertices are going to be the users and interest groups, while the edges are going to be the memberships or affiliations or hashtags. And so after we've already established our context, we would move over to really just focusing on matching the ciphering query, where we do so by matching users who moved from one interest to another, or subscribe to a hashtag, for instance. So we can say has hashtag and join interest. Has to be all caps, by the way. As those edges as well. So then the next part would be understanding the analysis in action. And mitigate faults and failures. We already know. Cipher the data. And look for faults and failures from hardware, software, and human side. And also consider scalability and reliability. Alright, there we go. So, let me just clean out of this for a second. There we go. And so, yes, this was ciphering queries within system design. Thank you again for taking time to be able to watch this. If you found this helpful, be sure and feel free to like and subscribe. And if you have any other questions, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we are going to be going over our system design course today, and today we're focusing on triple stores and Sparkle. So to be able to go over our concept, while graphs are the canvas upon which connections are drawn, triple stores and Sparkle form the paint and brushstrokes of semantic artistry and data representation. Well, what does that mean? The triple store model, often discussed in the same breath as property graphs. And leans on the triple's simplicity. There are three components really comprising of it. There's a subject, predicate, and an object. So if we were to go over here, so we have a subject, and so we overall have subject, predicate, meaning, location,
And an object could be referring to a person, or it could be the Mona Lisa in this case. And so this would just be an example really of what would triple stores and Sparkle really obtain. So Sparkle is really the language it's the query language. Designed for such data model. We weave queries that can pinpoint to precise information and traverse through a labyrinth of relationships and avail insights that could remain hidden within the confines of more rigid data structures. So it's overall great for traversing rigid data structures. And for those immersed in the digital world's connectivity, triple stores offer not just a repository, but a playground for queries that mimic the human thought process as that direction, tracing paths from subject to subject through a network of predicates and revealing a tapestry of objects, each a piece of a larger puzzle altogether. So strong connectivity overall. And now let's head over to our concept example. And now let's go over a concept example, focusing on the semantic web's quest. So let's imagine the semantic web as a grand library of Alexandria, where each book, web page, is not just bound by its cover, which is a URL in this case, in this example, but by the rich text it shares. So text would be the links. Overall, it shares with countless other ones. In this metaphorical library, we have RDF and Sparkle as the librarians. And they are organized the books not just by titles or authors, but by every conceivable connection possible. The librarian, in this case Sparkle, can answer not just what books are about Rome, but trace a lineage and ideas. So Sparkle, yeah, I'll just keep that right here. Let me just fix that. Can trace multiple connections based on a book. I'll put red for an example. All right. For instance, Rome, and then it can also go for Roman philosophy. And in a science text, it can be focusing on modern legal documents as well. And so, meanwhile, the RDF, on the other hand, will be applied whenever we are applying Sparkle to be able to call upon the different
subjects and ideas, and RDF would be acting as the card for each book to be able to act as a catalog. Tracer. Yeah. It's more of a card for the catalog of books in this example, detailing the subject it touches. So focuses on in-depth details. Such as every single object and subject that it's going to depict and reference. The semantic web overall is an ambitious attempt to be able to link across the globe in a decentralized manner. So link every it should be linking data across the globe in a decentralized manner. Turning the web into a universal database. So the web as a database. With the full version yet to be released, there's still triple stores and Sparkle still remaining a robust framework for interlinking data and driving applications that require a deep semantic understanding of the context. So what we have currently just that Sparkle and triple store. They remain a robust framework for interlinking data. For we know that Sparkle is allowing us to be able to go based on predicate, subject, and object. Let me just zoom out. And now let's head over to our first practice problem. And now let's go over first practice problem. So in our first practice problem, we're focusing on an academic research environment. In doing so, we have to conjure up an academic research network as our practice canvas. Here, researchers, papers, and citations are subjects. So we always need to know what the subjects are. Which are the researchers, papers, and citations. While the predicates are the relationships such as authored by, cites or reviews, and the objects would be research papers
papers, such as journal ones. Or any affiliations associated. There we go. And so once we have already established our network by identifying the subject, predicates, and then also objects, once we've already set up the relationships, we already have to use query connections as well. We're focusing on each of the steps that we've already set up in place. So we have one, established our network, and then we also construct the subject, objects, and predicates here. And then our query connections is ultimately just trying to connect the objects with our subjects and predicates as well, in terms of grouping as well by the references and number of citations and who the creator was in general. So yes, let me just move out of this. And feel free to take a screenshot, and we'll move over to our second practice problem. And so let's go over our second practice problem. So in our second practice problem, we are focusing on an ecological interaction network where species are connected by interactions, and prey on, pollinates, or competes with objects within the ecological system. So in such dynamic, we always need to know what the subjects are, the predicates, and the objects. Subjects in this case for ecological framework are going to be species. The predicates refer to relationships, always. Could be preys on, interaction, overall. And the objects would be referring to environmental features. Because if we focus on the species, we could be specific about animals, for instance. There could be ecological features such as plants within the whole area. And so after we have mapped the whole ecosystem and we understand the interactions, we need to construct a triple store that encapsulates each interaction. So I'll just move over here. We do so by constructing other species and other interactions as well. After we have mapped the ecosystem, we then need to understand the query interactions, and Sparkle enables us to ask which species are keystone to a habitat, allowing us to understand the flow of energy with food webs or assess the impact of invasive species. And then the third step, we have to understand the balance of the we need to understand the balance that the ecosystem depicts in order to be able to guide the conversational efforts and policymaking to preserve the biodiversity in the ecological system as a whole. So, over here. And so, yes, this was a brief concept overview and concept understanding of triple stores and applications with Sparkle. Thank you again for taking the time to watch this. If you found this video helpful, be sure and feel free to like and subscribe. And if you have any other questions as well, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye.
Hello everyone, today we're going over our system design course today, and today we are focusing on the concept of resource descriptive framework. Now, what is Resource Descriptive Framework, or RDF? At its core, RDF is a standard model for data integration on the web. So it is a standard model for web integration. But why is this important? Well, RDF has been based on making statements about resources in the form of subject, predicate, object expressions. So, based on subject, predicate, object expressions.
And these are called triples. So let's imagine a scenario where we have information scattered across different databases altogether. And each piece of information can be seen as a small fact or triple. So this is a piece of information. And it's considered a structure that includes a subject, a predicate, and an object. For example, with the color blue, can be broken down into the subject, such as the sky. Let's put sky right over here. A predicate is, and then the object, blue. In RDF, these triples are used to make assertions about resources, anything that one can think of that could be identified using a unified unique identifier called a URI. Unique URI. And this system allows data to be mixed, exposed, and shared across different applications. RDF triples can be written in various syntaxes such as Turtle or RDF/XML. Can be written in RDF/XML. Let me just make this clearer for you folks. And Turtle as well. And Turtle is a more human readable format, making it the preferred choice for many. For those who need to work with machine-friendly code, RDF/XML is an option, and there's tools such as Apache Gina. Which can convert the data between these following formats, making RDF flexible in general. The real magic of RDF overall comes from its foundation in the concepts of URI. This means that anything defined in an RDF triple can be a web resource, providing a global way to identify anything we talk about. And this is crucial in linking data across the vast expansion of the internet. If we were to have a following search of queries as well, it overall allows us to utilize RDF to facilitate web data of what might call the semantic web, and where data can easily be integrated regardless of where it originates from. And now let's head over to our concept example. Let me just clean this up for you folks. Yeah, it's Gina, Jena. There we go. And feel free to take a screenshot before we move over to our concept example. And now let's look at a concept example. So suppose we have a website that provides information about different countries and cities. In one database, we have a city for Paris, namely, and it's tagged with the country France. So we have an RDF file for cities and locations. So in this case, in this example, we have Paris as a city. Then we have France as a country. And then in another case, we may have Paris also integrated with sightseeing. And overall, the RDF allows us to be able to merge these data sets seamlessly, given the fact that they're focusing on two different subjects that we have. Really, just even though that they are related with Paris, the city, we also have France as a country, and then sightseeing as well. Now, if we want to create a comprehensive guide for tourists about Paris altogether, we would need to gather this information about the country and the attractions it offers. Instead of manually searching each database, we instead are able to integrate this information altogether to create a richer experience, and without that much extra legroom. It's the beauty that lies in the RDF's ability to use URIs. So this is all leveraged using URIs, which give every single piece of information as a unique identifier that could be referenced across the web. And it doesn't matter if one database uses a symbol for France in particular, like FR, to refer to France, and another person to use French Republic, as long as they are tied within the same URI. As long as they are associated within the same URI, they are able to be in the same RDF altogether. And this is the foundation that brings us data exchange, is mostly in the power of the URI. There we go. And now let's head over to our practice problem. And now let's go over our first practice problem. So in our first practice problem, let's consider the scenario of developing a smart library catalog system. This library wants to offer a service where users can search for books not only by titles or authors, but also by related subjects, published years, or even language. So you have a smart library that wants to figure out how to search for not just titles, but also include related subjects, published years, and languages. To achieve this level of detail of data integration, RDF model would be deployed, and with our following tasks, let's just go over our RDF file that we have. So let's go over our first one to be able to help understand. So let's call upon the example of The Great Gatsby, for instance. The author would typically have a URL, or URI, sorry. The author would have another URI, such as F. Scott Fitzgerald. Similarly, we create URIs for each year, language, and category. So we have the year, language, and then category as well. So all of these are separate URIs. But they are integrated. In the RDF format. All the URIs are integrated, and so what we are doing is that once we have already created triples, namely such as creating the title, creator, date, language, and subject, which will already have our subject, predicate, and object, we will be able to integrate all of our information into RDF. So in RDF, to avoid writing out full URIs every time, we use a namespace DC, namely, just to go over, which is a common naming prefix standing for doubling core, a set of vocabulary terms used to describe web resources. And overall, by following these steps, we're able to create our RDF file for the library. And this is just a concept overview for a specific example for an RDF file.
And now let's go over a second practice problem. So let's focus on the scenario for actually dealing with personalized music recommendations. So in this practice problem, we're considering a music streaming service. So we're doing a music streaming. That wants to provide personalized recommendations for its users to tailor recommendations. The service needs to understand the relationships between musical genres, artists, albums, and individual songs. So we already need to know what our subject, predicate, and objects are. So the subject would be the listeners. The predicates would be the relationships with the songs. And the objects would actually be the songs, the actual songs. So the relationships for the song could be taste, preference, or it could be other varieties depending on what aspect of music they are looking for. Maybe an individual artist, or maybe a specific genre in particular. The predicates can go on for a countless amount of selections. So overall, we are focusing on developing a RDF model that includes a new album called Jazz Vibes with the artist Ella Fitzgerald, which features songs from jazz and was released in 2021. And this allows the same steps as practice problem 1 to build our RDF triples, because every aspect of data is going to have subject, predicates, and objects. And so if we were to go further in depth inside of our script that we have over here, we notice in particular that we have our album, then we have the artist as well, and the genre, and also the album year as well. So in this case, over what we have is that we are creating our RDF file based on one, aside from the triples of our following information, based on the album, artist, and genre, and also release year as well. Because we can have multiple predicates inside of our triple as well, as long as we're able to differentiate between what the subject, predicate, and object are. So the subject will be the album, the predicate will be the relationship of the album, and the objects could be artist, genre, and year. Again, the objects can go on for many, many situations. We just have a main subject that we're already focusing on in this triple, and every single component of the RDF file is going to be comprised of URIs, which differentiate them. So we have URIs to differentiate, and also we have namespace such as DC right here. To simplify our triples to ensure we don't have to write out the full URIs every time. And so yes, this was RDF, or Resource Descriptive Framework for System Design. Thank you again for taking time to watch this. If you found this video helpful, be sure and feel free to like and subscribe. And if you have any other questions, feel free to put it in the comments section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to be going over our system design course today, and today we're focusing on the concept of graph databases. Now, graph databases are designed to handle complex and interrelated data in a way that's more intuitive than traditional relational databases. The key difference is their ability to manage many-to-many relationships. So, able to manage many-to-many relationships. And overall, their dynamic scheme is flexible and is willing to change. Unlike their predecessors in the Codicil network model, graph databases don't have strict schemas, and there's a way more flexibility to be able to add in records that can be nested with a flexibility of order, unlike traditional predecessor of codicil, where there needed to be a specific set of order of record types. So overall, there is greater flexibility with graph databases. You can have more parameters, for instance. Such as maybe new ID content, whether name, age, sex. It's very flexible to be able to have those relationships and add them on, such as if we were to give an example of social media networks in particular. So, for instance, friend groups, when one is able to sign on a social media platform and you want to search for your friends, chances are that there is a set criteria already set up in place where focusing on age, school, location, where you're able to find your friends and connect with more people and such. Graph databases have a key application, for instance, in graph databases and use cases. And another major advantage of graph databases over codicil is the lack of mandatory ordering for recording children. Children can be added on dynamically, so children can be added on dynamically. And there is no ordering required. Because we mentioned in the previous series of lectures about codicil, it required a set order in place based on hierarchy, but in graph databases, as well as what we talked about in graph models, graph databases have wider ranges of flexibility. That's the main idea that we're getting in this part for our concept overview. And overall, given the flexibility, they modernize querying by supporting high-level declarative query languages such as Cypher and Sparkle. And we also know that declarative is always focusing on the what, as usual. So the flexibility equals greater support of declarative, also known as the what for querying. And overall, it's pretty hard to be able to, especially focusing on really strict relational databases for set querying, because you have to go through a series of steps, and therefore it will become inefficient if you ever have a computation to be able to search through specific forms of data. And yes, so that's our concept overview for graph databases. And it's just a brief overview. Let's go over our concept example. And now, to solidify our understanding, let's go over our concept example. So to fully understand graph databases' flexibility and power, let's consider a real-life example of a social media platform. In such a platform, users can form connections with other users, join groups, post comments, and interact with other posts. So flexibility provides wide range of functions and added data, and the many-to-many relationships inherit this environment of interaction, like a user belonging to multiple groups or posts being tagged with various topics. It's overall pretty intuitive inside of a graph database. So just for an example, users interaction with different groups. Or tagging in posts. In a graph database, each user, post, group, and topic could be represented as vertices. As we know from our graph model lecture, we know that graphs typically have vertices and edges. Edges focus on the relationships, and vertices are the subjects. So we have subjects. And relationships. With such, subjects can be users, posts, groups, and the edges for typical graphs are the connections of relationships. And when a new user joins the platform and starts forming connections, their data can be easily integrated without redefining the entire database schema. So easy integration. Searching through this network is equally efficient. If the platform introduces a feature to search for users who belong to certain groups and have interacted with specific topics, a graph database can handle this through simple queries that traverse the network via declarative declarative statements, easier search. And integration. And searching through this network is overall efficient. If a platform introduces a feature and such, a graph database can handle this through simple queries and traverse the network, irrespective of whether the connections have started in a given state or time. There we go. And now let's head over to our first practice problem. And now to go over our first practice problem, imagine a social networking service that allows users to follow others and engage with a variety of content types. The data system behind it must map intricate relationships among users, their content, and the interactions on that content. So we need to map intricate relationships between the vertices and edges. When we have already determined exactly what our subjects are, along with their relationships, we can map out and construct a graph database to make various queries and such. A graph database overall will be efficient to store and query these complex and intricate data sets. So mainly what we would have to do is that we need to create a graph that represents the following scenario. And so in our pseudocode, what we have done is that we're calling upon a graph database in this case, and we are putting in the relationships that user A follows user B. So we have user A follows user B. User B creates a post. User A likes and comments. User B's post, and user A shares user B's post. Then user C sees it. And so we have pseudocode already over here that already understands relationships. So for instance, we have already highlighted. I'll just number these as well. So once we have already created user A, B, C, and then post as well. So we have a post by user B, and then here we have a relationship that is already set up with our users and our post as well. So we create edges to represent the relationships once we have already created vertices. These are our edges, which dictate the relationship as we have already known. So this would be considered a vertice. So I'm sorry, this would be considered an edge. This would be considered an edge. Likes and comments, another edge, and then shares, then user C sees it. So technically you can say that the edges are also the actions which define the relationships. Yep, and as we know, vertices are the subjects. So that would be users, posts, comments. And so we have already defined that the first thing that we always need to do, let me just put this over here, is that for the graph databases, we need to, one, let's move over here, create the vertices. The second one is create the edges. Then after we have done so, what we would do is then query, as we see over here, for any extraction of data, so with declarative programming. So we query with declarative programming. To be able to match the user's posts, shares, and creates between the intricate relationships we have already established. And once we have already constructed the following graph, we can query all of our following data that we have already set in place. And so this is just an outline between our first practice problem. Let me just zoom out so we can get a clearer understanding between everything that was just made. 1 second. All right, now feel free to take a screenshot, and now we will move over to our second practice problem. Then for our next practice problem, let's consider a project management tool where users can create project tasks and assign tasks to team members. So we are mapping the relationships between project tasks, assigned users, overall. We can discern, since we're mapping the relationships between the project tasks, and users, we already know that we have the following vertices, which are considered the subjects, and always the edges are relationships, and they are defined by actions. When we have done so, we can already discern, just according to the pseudocode that we have, we can discern the following. So one, we have to consider our number of users. So in this case, we are going to have user D create a project, create project X, with the next one being that user D assigns tasks 1 and 2 to user E for project X. And number 3, we would have user E mark tasks 1 as completed, and then we have user F observe the project completion, the project X completion. So we can already see, namely, and when we go over our steps, we always need to know exactly, one, we need to create our vertices, then we have our edges that are over here, and we assign when a task is already completed. So the database's caching queues are already updated, because every system design, every system needs a database caching queue to be able to have their data stored and interact. And then we will be assuming a simple rule that each task completes the following progress. Here in this case, we're going to have 50%. For task 1 and 2, we're assuming a simple rule that each task completion has 50% progress, and we're going to update the progress accordingly in our database. And then user F observe project X completion by a query. So we have a query. So vertices, edges, and project progress. And then we already print our following query. So the steps in order to be able to map out all of our following relationships. There we go. So as usual, 1, we need to define the vertices, which we already have discerned based on following users, project tasks as well. Then define the edges. And then have status updates and queries. All right, and so yes, so this was our system design course video series on graph databases. Thank you again for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions as well, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we will be diving into our system design course today, focusing on databases, storage, retrieval, and indexing. So in today's lecture for the world of databases and focusing on the fundamentals of storage and retrieval and indexing, at the heart of it, a database's purpose is twofold. 1, it stores data. So I'm just going to put databases store data, as we all know. And the second part is retrieving. The stored data. So we can think of it as an incredibly well-organized librarian who not only knows every book, but also remembers which book you borrowed. Knows every piece of storage and history of storage and retrieval. Just fix this really quick. For developers, understanding a database's internal storage and retrieval mechanism is key to knowing the workings of the car's engine. It's not just about making it run, it's about tuning it to peak performance for whatever race the car's on or whatever application the database is being used for. Some databases are like sprinters, optimized for transactional workloads. So there are different databases. For different purposes / application. Stock trading platforms, for instance, would use speed, so fast transactions. That could be just one case. Other applications of other databases could be like marathon runners, designed for analytical workloads with stamina to handle large volumes of data over time, also known as analytics. So we can metaphorize both of them as like a sprinter versus marathon runner. They're both athletes, but they serve different purposes. / environments. Within these different forms of databases, there's a subset of storage engines as well. There might be another different variation of them. We can have a different series of them depending on whatever application and variety of use cases will be used for databases. There are, for instance, column-oriented storage engines in one example, and they're good at analyzing processing in particular. So overall, the main concept that we're just trying to get over here is that there are different databases for different applications, and they also have different means of storage, retrieval, and indexing. We'll be going over our concept example and our 2 practice problems as well to be able to help solidify our understanding. So let me just zoom out just a bit. Let's clean this up. There we go. And feel free to take a screenshot of this, and we'll move over to our concept example. So now let's imagine that we are building a new social media platform. It's going to handle millions of users who will be sharing and interacting with a multitude of posts, images, and videos. And our choice of database is going to be very critical. For the high-speed interactions, such as shares and comments, namely, you can do a transactional database. So really the main concept that we need to say is, hey, what database are we going to use? If we're going to go for speed, most of the time we're going to do a transactional database. And really the point of it is to be able to understand the activity and efficiency of how we can apply that database on said activity. However, if we want to analyze user behavior to tailor the feed for target audiences and advertising, we can do a column-based, so anything related with analysis. We can do a column-based database. So column-based or column-oriented based. Same type of principle. So now, if we're going to be able to strip down to the basics with the world's simplest database, which uses 2 bash functions to set and get, as our example over here. So if I want to zoom in, this is the simplest database. Overall, all we're doing is just doing a set and get, which are these two bash functions to illustrate a key value storage. So this is also a key value storage. We can input any data, maybe like a JSON document, and retrieve the latest value associated with the key, namely. So in this case, this one looks like it's going to be the key over here, and to be able to implement inside of our database that we have. It's overall, the set and get method in the world's simplest database is simple and quite efficient. It's akin to jotting down notes in a pad. However, as time typically goes on, as we know within our next, I'm actually going to make this one and put it down below to be able to illustrate more, because really we're going to be focusing on the complexity as all this is going down. So as more notes are added to the pad, the notebook in of itself, in a metaphor, so we can think of a database as a notebook. And you can write anything in it, and you can put any form of data that you really want. However, the type of notebook, depending on what you want, maybe there might be like engineering notebooks, maybe art notebooks, maybe you're doing it for video in that case. It can be anything, but again, they have their different forms of applications to already be set in place. And sometimes the more data or notes you typically put in, the more complex and more intricate it's going to take for that notebook to be able to actually store and manage that data, and also be able to quickly retrieve it at the same time. Because if you're writing in more notes inside of a notebook, for instance, and you need to search out the key concept, it's going to take a long time to be able to find it as the notebook becomes thicker. So overall, we would have to think about different applications for different cases of considered notebooks or databases that can fit well within our application, that will make it more efficient and be able to store and retrieve our data with proper indexing as well. So we need to focus on efficiency of storage, retrieval, and indexing. Let's just move this up. I'm just going to clean this part up so we can see the whole thing and you can take a screenshot. All right. Okay, and now let's head over to our first practice problem. Now to go over our first practice problem, let's consider tasking with improving the search efficiency of a growing e-commerce platform's product database. When we do so, the database is a straightforward key value storage. So base, simple key value storage, where each product's unique ID is the key, and the value is all the data related to the product. So actually, product details is the value. So product details is the value. And we'll notice that finding a product over time, as we continue to add more, typically gets slower as the inventory grows. For we already know, like databases are just like notebooks. That's the best way of describing it. And as you add more to the notebook, it's going to get harder in particular to be able to find information, since the notebook is already filled with more and more information over time. Similar preference within, and similar dynamic with databases as well. And in order for us to be able to address more information, we need to create an indexing structure that accelerates the retrieval process. So we create an indexing structure to accelerate the process. So this is just a simple product ID that we already have, and then this is also in the case of searching for a common product to create, to be able to get a product's name relative to their ID. And it could be, for instance, a product type, product value. So this is our key that we have, and the name will be considered the value. And this value is also interchangeable to other components whenever we're doing a key value pairing. So the steps for us to be able to actually go through and create a robust indexing is that the first step, we need to design the index, assign the key value pairs, and the next part is to implement the index, as we've already seen. And the third step will be improving indexing. It's pretty straightforward. So a lot of the times when improving indexing and maybe enhancing space and time complexity, for data retrieval. Implementing the index is pretty straightforward. Let me just clean this up. There we go. And alrighty then. Let me just move this over. Alright, feel free to take a screenshot and we'll head over to our second practice problem. And now let's go over our second practice problem. So in our second practice problem, let's shift our attention to a public library's digital archive. This system stores thousands of digital books, each with a unique identifier. So there are thousands of books. With unique identifiers, or IDs, we'll just put it right here, and associated metadata. Typically, we already know exactly between what the key is. I'll just use a different color in this case. It'll be a key, unique ID, and the metadata are the values. And the problem is similar to the previous one, and we already note that databases are like notebooks, where as the archive grows, patrons find it increasingly slow to locate specific books. Complexity overall increases, so complexity increases as more data gets added. So I would say complexity increases with search / indexing. There we go. And so if we're able to go further in depth in terms of our example with what we have, in order for us to be able to actually figure out how to search and index properly throughout this specific database, so the library's database is slow because every book starts with in this case, in our example, we're going to have is that we need to find the most efficient way to search and index our database. Unfortunately, in this case, in our example, the library is already stretched out between books with titles ranging from A to Z. However, there are more efficient ways to be able to actually index throughout the given database, such as we can have multiple parameters to search for specific knowledge. So we would have to implement multiple parameters to search for a specific book. When we have done so, we can then know exactly how we could design the index and implement the index. So if I'm just going to create some extra space over here. Give me 1 second. There we go. There we go. So, first step that we would typically have to do would be the following. 1, design the index. When we have designed the index, the index needs to be particularly sophisticated, namely because we will have to consider the parameters. So consider parameters to search for specific book. Then the next one will be figuring out how we improve. So improve the index. In this case, since we're using multiple parameters, since we have different subjects of title, author, and subject, these are all considered different keys. So these parameters are keys. And the value is always considered their metadata. So going back to the first one, we would consider our keys and values. And when we implement the index, let me just clean this up. Since we have a multi-key indexing system, we can think of different forms of algorithms to be able to apply. So we would apply different algorithms to search and index, search/index. A number of examples that could work. Be B trees. Since they're multi-keys. Maybe we can even put in a hash map. Or even a graph tree. Just to name a few, as a few ideas. So put this right here. After we design the index, we then implement and improve. Okay. Implement. Create the index. All right. So yeah, this was our system design video lecture series focusing on databases for searching, retrieving, and indexing. Thank you again for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions as well, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye.